All right, good morning, everybody. All right, welcome. I know folks are still grabbing snacks and coming in, but I do want to just kick things off. Welcome, everybody, to Schoodic Institute. Welcome to Acadia National Park, and also want to acknowledge we are on the vast homeland of the Wabanaki, and it's really great to be here with you all today. I'm Nick Fisicelli, President and CEO with Schoodic Institute at Acadia National Park. We are back in person and also virtual, so thanks for joining us either right here in Moore Auditorium or from your sofa at home. And no surprise, there's been lots happening the last few years. The pandemic has kept us from doing this in person. So it's been 3 years since we've been able to host this. And so lots has been happening. Rapid change in Acadia has not stopped during the pandemic, but also the science in Acadia has not stopped during the pandemic, and you all have not stopped during the pandemic. So thank you all for continuing with the science, continuing with the stewardship here in Acadia through these definitely big changes. And that's a lot of what the research is about here in Acadia. It's about rapid change and lots of uncertainty. And that's something we've all experienced in lots of ways, both professionally and personally over the last few years. And the pandemic continues. So thank you all for being masked here in person when you're not eating. And we are following National Park Service guidance on COVID, and right now for Hancock County, where we are located, the community COVID level is high. The red level, it just changed last week, and so we are back to masking. And Kevin Schneider, superintendent with the park, will be joining us here later this morning. He has an unavoidable meeting, but he'll be welcoming you all, or actually being part of the closing at the end of today's session, and really is excited to be part of this today. And we get to travel all over Acadia today without leaving your chair here in the auditorium, or again, your comfy sofa at home. And so we'll be in the forests, we'll be in the coastal headlands and at Bass Harbor, we'll be on Otter Creek here on the Schoodic Peninsula. We'll also get out slip sliding into the intertidal zone today, and we'll even get a little bit more wet and wander out into Frenchman Bay. And we'll be hearing from scientists and resource managers today from the National Park Service, from UMaine, from Schoodic Institute, from College of the Atlantic, the town of Mount Desert, and Bowdoin College, and then also the Penobscot Nation. And Catherine Schmidt, who I'll hand this over to, will be the moderator for our session today. And Sarah Lucchini, who you may have seen when you checked in, will be taking some photos during the sessions today of all of your beautiful masked faces. And so if you don't want to be in photos that we share, just let her know, and we can take care of that. Please remain masked in indoor spaces. And with that, again, big welcome, and I'm going to hand it over to Catherine.
Thanks, Nick. Thanks to all of you for being here today. Thanks to those joining us on Zoom. It's my pleasure to help keep us on time today, to give instructions, including just a couple of housekeeping things. Restrooms are out here and to the right. We do have information out on the front table about Second Century Stewardship Fellowships, as well as anticipated opportunities for early career scientists for the 2023 season. So please, there's a couple flyers on the welcome table. There's also, so the poster sessions are going to alternate with our presentations this morning. And our first session, and all of the sessions today, you know, Acadia has this incredible legacy of science. And what that means is that we have a lot of different baselines and historical records and studies that we can repeat to see how things have changed. And really, I don't think there's any other park that has that extensive of a record of historical information and data on landscape and seascape changes. And so today we're going to hear from people who are doing those studies of change. And our first session is about forests. And so it's my pleasure to introduce Vic Wheeler, who's a biologist from Acadia National Park, for our first talk of the day. I am going to keep us on time, so you'll see me standing up when it's time for the speakers to wrap up.
And then you'll see me talking very fast. Thanks, Catherine.
I think you're all set.
Okay, thank you. Let's see here. Got the fancy. All right, we're set. Thanks for coming, everyone. So I want to talk about bird behavior, ecological theory, natural history, how it all comes together, smushes together at Bass Harbor Head. And so Ken Kroll, who is a brilliant scientist just down the coast from here, did a lot of work on island biogeography, said to me that science is a journey. And from that, what I take from it is that science as a methodology, which tries to impart objectivity and keep us honest, the journey component adds the story and the context, remembering that people do science, that science is based in society, and science cannot be in isolation. It needs to be within the context, however, trying to keep that rigor all along. And so Robert MacArthur, who lived from 1930 to 1972, was credited with many foundational developments influencing fields of ecology. So this includes community ecology, island biogeography, theoretical ecology, and really took the field of ecology from a descriptive practice into introducing experimental designs. MacArthur's dissertation, which launched his very short but impactful career, was based at Bass Harbor Head. And the premise of his study was, how do we have so many species in the same place without them out competing each other? And so here we have a family tree of the genus Setophaga, which is about 34 species of wood warblers. So little dinky birds. They all look about the same. They all kind of fly around the same. They all kind of eat the same stuff. And so if we think about it as, if we have 5 species of this genus, all at Bass Harbor Head, and they all are doing about the same thing. They all have about the same environmental requirements, or what we would call a niche. They are, we would logically have competition between them. Okay, so if we have the species, we would have a best forager, a worst forager, and the worst forager would go extinct. And then sequentially on until we just are left with one species remaining. And so we'd have the reduction of species. However, the paradox is that we don't. We have a whole bunch of species. And so why do we have species in the first place? And then why do they maintain? So the way that MacArthur answered this in his studies at Bass Harbor Head is taking what's really an idealized tree. And so the way that you read these figures is, this is a very triangular, very classic tree form, as my 4-year-old would draw. And what MacArthur did was he observed warblers foraging in the trees at Bass Harbor Head. And he assigned each foraging event and time and frequency to a location. And so there's vertical stratifications. So these are 10-foot sections of the tree. And then we also have these sections radiating from the stem or the trunk. And so we have this middle bare branched area of a spruce tree. We have this leafed in area, and then we have the tips of the leaves. And there are some numbers on there, and these are percentages of frequency and then of seconds. And so, but MacArthur kindly shaded in the top 50% of these foraging events. And so the way that he answered this paradox of how we have so many species without outcompeting each other is that they were actually partitioning the resource spatially and behaviorally. So we have these are 5 different species of warblers, and each one is utilizing the same trees in different ways. So we have here the yellow-rumped warbler using the bottom. We have the bay-breasted using the middle. We have Blackburnian, which is sort of on the outskirts here. And this allows the birds to not outcompete each other. So why are we talking about this like over half a century later? And it's a good question. The reality is that the field of ecology has really, really embraced this explanation and has really embraced competition as a mechanism for species maintenance. And it's formulated a lot of theory has come from this. This is really a basis. It's also become ubiquitous in textbooks. And so here we have a textbook which looks a lot like the figures that we were looking at before that MacArthur drew. They removed those pesky numbers. So it's just, you know, the shading, a little bit of color. It's nice, monochrome still. And then we have the next iteration where we've got a little bit more of a stylized tree. I'm liking where they're going. They've taken away all of those zones that aren't used because really we just care about where they are. And of course they have these nice little pictures of the actual bird. You know, these are advancements. You know, and then we just kind of jump right into, let's go ahead and just draw it how we want to see it. And here we have the bird placed right where it is. You know, the black-throated green bird only forages on the right side, the Blackburnian only on the left. And really there's no data here. It's just a little bit of like, here's what we kind of think would be neat to see. I love it, don't get me wrong. So the other thing is that this has set the stage for countless studies across the globe, across taxa. It isn't just birds at Bass Harbor Head and spruce trees. And so why did I repeat the study? And so despite all of these studies having already been based on it, it's never actually been repeated in the same place. Like Catherine was saying, this is sort of the basis, and this is what the luxury that we have of having this legacy of data just sitting around waiting to be looked at. And so repetition is really critical to foundational studies, right? Because this is how we advance theory. This is how we solidify or change theory. So I looked at quite a few components of study there, but it was including, so prey distribution, which matters if you're thinking about how warblers are foraging and where they're foraging, matters that it's homogeneous. Also warbler density and distribution, if we're talking about competition, there needs to be enough warblers and they need to be in the same place, right? Also looking at forest structure, which some other folks are going to talk more about, so I'm going to leave most of that to them. And then the foraging behavior, and so looking at that sort of classic tree representation. The forest structure, as MacArthur described it, was a stand of white spruce, approximately 60 feet tall. They're all about the same. There's a uniform tree. And MacArthur was thinking this happened because there was an agricultural field at the site previously. If I were to describe the site in one sentence, which I have not done, but I'll try, I would say that it's there's a lot more red spruce than white spruce. There are a lot of different ages, different densities of number of trees in space, depending on where you are. It's very patchy. So in my long sentence, I think it's a little bit different, but things change. And that's what's interesting about this. So looking quickly at a couple of species and how they're foraging and niche partitioning between MacArthur's surveys and my surveys. Here we have the yellow-rumped warbler, MacArthur's drawing, and then my updated drawing. And then we have black-throated green here, and MacArthur's drawing again, and my drawing again. I did not stipple as well as MacArthur, I'll admit it, but I tried. So what's happened here is here's MacArthur's partitioned and yellow-rumped warbler down here, and then black-throated green up here. And what I saw between these is a change. So we have yellow-rumped warbler at the bottom, and I saw them up at the top. We have black-throated green at the middle outsides, and I saw them on the outsides, yes, but more at the top. And so what we have is a change in behavior over a half a century or so. Additionally, looking at the warblers that were present when I did the surveys, black-throated green, yellow-rumped warbler, magnolia warbler, and northern parula, they all pretty well occupy these upper portions of the spruce tree. And so what we have is we do not have a strong partitioning, each species having a separate zone. So we're left with, what do the changes mean for this theory, right? And for me, it's behavior is extremely plastic. So it's several generations later, but the behavior of these species is not the same as it always has been. And presumably it can change again. And this means that niche partitioning is unlikely to be the sole reason for the divergence or maintenance of these warblers. So how can so many species coexist in the same place? And while it is possible that partitioning only happens in those very high densities, this is perhaps there is a plastic behavior that they fall into and fall out of, but we would expect that once they partition, they would continue to do so, especially if it's that sole mechanism for maintenance of diversity. So we are indeed left with, why do we have so many species, right? This is a question that persists today. And for me, it really comes to that it's the journey of science, that it's a story. It brings theory and history and data and repetition all together. And why we have so many species is still a valid question that still needs more time and effort to dig into. So with that, Catherine's not hovering, so that's probably a good thing. Thank you.
Thanks, Vic. We have plenty of time for questions. We are gonna bring mics, so just raise your hand if you would like to ask a question, and we need you to ask it on mic so that our friends on Zoom can hear it. And then we have some time to see if there's any questions on Zoom. So I did see a question over here, and thanks to Olivia Milloway, Science Communication Fellow, who's gonna help run the mic today.
Hi, I'm Maya, the Science Research Fellow at Acadia, or at Scudic Institute. And I was wondering if climate change and human activities are going to increase partitioning by increasing the density of species in an area, or if it will decrease partitioning because of increased competition between species.
So these all depend on what type of competition we're seeing here. So if it's density dependent competition, if it's density dependent partitioning, then I think yes. However, I think that there's also, an underlying factor. And for me, and I've not covered this in these studies, but being a warbler is really tough. It really is. I mean, not only are you competing with your neighbors, right? But you've got migration, which is extremely energetic and high mortality. You've got predators, whether it's a red squirrel or a peregrine falcon, anthropogenic noise and light and windows. It's really tough to be a warbler. And so, getting to those densities, what is that threshold for that density to be too high? And that's something that is difficult to find, but also there's so many compounding factors. For instance, there was speculation that during MacArthur's surveys that there was an outbreak of spruce budworm, which is a forage source that can be utilized and is at very high abundance at that time and then very low abundance later on. And so these are things that can reduce competition and then also increase it later on. So we get these really differing, there's a lot of knobs and levers to turn, and so it's tough to point to just the one. Additionally, there is thoughts about if we have interspecific or intraspecific competition between species or within species, and your niche overlap of your own species is extremely high. And so we do have these varying levels and degrees of competition leading to varying levels of influence. I don't know if I completely answered your question, but that's where I'm going with it.
Hey, Dick. Did you also see a change in composition, species composition in that forest stand?
Yes, is the short answer. The long answer is in a couple of ways. There's there are different species there present. MacArthur did not record all that was there, and so I don't have a full list of what was there during MacArthur's time. But there has been some turnover. Additionally, the entire genus was reclassified in 2010, and so there were actually more species added to the genus in between the two. So there's a lot of, and that's where it's the context and that's the story, right? Is that they were Dendroica, right, when MacArthur was there, and then by expanding and combining several genuses, then we end up with a whole nother suite of understanding how they're related. Cut me off? You can, it's okay.
What we got on the agenda today? Oh, great. So what will be there today? Oh, great. Very nice lady.
So the question was whether there is, if behavior is plastic, is there a learning component to a species knowing which tree it ought to be, or which portion of the tree it ought to be in? And there's actually some really great studies which are on my bucket list, but we'll get there when we get there. But to cross-foster some of these birds. And so what you would do is you would take chicks from one species and chicks from another species, and you'd plop them into each other's nests, and you'd let the parents rear those chicks, thinking that they are a goose when they are indeed a duck. And what we end up with is an answer as to how far this plasticity can go, and whether there are morphological constraints or whether this is purely a learned behavioral phenomena, and whether it can happen within that one generation. So I do think that there's learning. I do think that there is a high degree of plasticity, and it can happen within a generation or between generations. So, but we still need to cross-foster some chicks. Okay, I think that's it.
All right, thank you so much, Vic. Next up, Jay Wason from the University of Maine is going to tell us a coastal spruce story from Acadia National Park.
Thank you, Catherine, and thank you everyone for being here today. So my name is Jay Wason. I'm an assistant professor in the School of Forest Resources at the University of Maine in Orono. And today I'm going to be telling you a story of the spruce forest that many of us know and love along the coast of Maine. And I want to start by certainly thanking some of the folks that have helped make this work possible. So this is Sean Fravor, who's an associate professor with me in the School of Forest Resources, and his graduate student, Camilla Syrup, who also works for the Park Service to make sure this is actually part of her graduate research, and they've been really integral in making sure some of the work that I'm talking about today was able to get done. A lot of people helped to make this work possible, from some of the initial ideas around resurveying some of Ron Davis's historical forest plots, which I'll be talking about, graduate students that contributed, and of course the funders that made this work possible, including the Second Century Fellowship. So today I'm going to be telling you a story. It's going to span centuries and generations. Like all good stories, it's going to have death and destruction, but it's also going to have growth, rebirth, community. And it's going to hopefully have a personal connection with each one of you. Whether this is your first time to the coast of Maine or whether you've spent years and years and years here, you can all connect with the story of tree RD85. I had no idea how that was going to go over, so thank you. So tree RD85 is pictured here with RD85's family, and this is a picture of RD85 from the 1940s. This is where I'll pause and say that I'm going to use some creative liberties today when I'm talking about RD85, but all the information I present around the science of our forests and how they're responding to climate change will be the best science that we have today. So you'll see me kind of tweak it though a little bit to weave RD85's story through this. So unfortunately, RD85 is dead. And so this is kind of the lead into the story. So here's RD85. You can just barely see that long linear transect there with moss growing over it and the rocks left over from when RD85 tipped over about 50 years ago. So this is kind of the lead into the story. Now to really understand RD85 though, we should really try to understand how RD85 got here. And to do that, we need to understand its ancestors. So this is where we go back in time 12,000 years to think about the coastal forests of Maine, in particular, Mount Desert Island and Acadia National Park. So this graphic on the y-axis vertically is representing years before present. So at the top of that graph on the left-hand side is current day, and at the bottom of that graph on the left-hand side is 12,000 years ago. These different charts tell us how common different tree species may have been in these forests at different times based on pollen records from those different genera. And we can see some important patterns. This is actually from Blackwoods, those of you that are familiar with this region of the park. For about the last 2,000 years, red spruce, which is RD85's ancestors, or the species that RD85 is, has really been common in the park. And this is what many of us think of when we think of coastal forests in Acadia National Park. But that hasn't always been the case. You can see that for about an 8,000 year period, pine species were really common, in particular white pine. And so our forests looked very different for much of their history. And there was even a period of time for about 6,000 years where oak trees were common in our coastal forests along the coast of Maine. And so this is important context as we think towards the future, but it demonstrates that they haven't always been the beautiful coastal spruce forests that we're often used to thinking about. RD85's ancestors thousands of years ago had to work really hard to finally gain a foothold in this system that they now dominate. So let's think about how RD85's ancestors might have done that. This picture here shows a little red spruce seedling competing with a white pine seedling you can see in the background there. And so what actually happened during this time period was some climate changes that were key to allowing these spruce trees to survive. They're really sensitive to temperature and moisture. And so there's a period of cooling and increasing moisture conditions that allowed RD85's ancestors to get a foothold. These red spruce trees now could regenerate in those forests. Many of you, if you spent time along the coast, are familiar with the cool and moist conditions like we're even experiencing this morning, and the coastal fog. Those conditions can help to nurture the regeneration in the understory for these trees. And this is one thing that we're monitoring when we study our coastal spruce forests is the understory climate conditions. And so that little white plastic cup has a temperature and humidity sensor inside of it. And that can tell us how the climate is changing in the understory of these forests where we grow the next generation of our trees. So this is kind of thinking about how we got all the way up to today with RD85's ancestors getting into this forest system. Now let's move into RD85's life. So again, I couldn't take an increment core, those of you that know that strategy, from a dead tree laying on the ground that's that decomposed. So I'm using an increment core from another tree that actually grew along the coast of Maine to represent this growth. Here we're looking at 1850 to today on the x-axis, and the y-axis is representing, you can just think of it as growth, but it's really diameter radial growth of the tree. This is RD85's life. You can see that there were times where things were really good for RD85. Things were going great, but there were also some really, really low points in its life. There was a period from about the 1940s until about the 1960s or so where there was a steady decline in the growth of that tree, maybe a burst of growth near the end, but then it died and tipped over. So while this may be a sad story from the perspective of RD85, we all know there's other trees in the forest. And so this is an increment core, so these are represented by growth data from a neighboring tree, RD85's neighbor. So while they shared some commonalities in when they were growing, there's also some differences. When things were going well for RD85, things may not have been going well for its neighbor. There's some competition going on there. There's some shared challenges, like around 1920. Many of you may be familiar with what happened in the 1920s along the coast of Maine. There was a major spruce budworm epidemic that occurred. And so that outbreak caused a reduction in the growth of a lot of the spruce trees that were impacted by spruce budworms. So that was a tough time for all red spruce trees and Mount Desert Island. They also both went through that decline in the 1940s to 70s, but after RD85 died, that opened up the canopy a little bit and allowed this new tree, RD85's neighbor, to achieve unprecedented growth rates for that tree. And you can see that's happened a few times for this tree, really high growth rates. This is a picture of the graduate student Camilla Syrup working on this project, drilling into one of these trees, and you take out a little pencil of wood, basically, and you can sand it down, and this is actually representing the growth rings that you can measure to do that. And so we talked about the 1920s with that spruce budworm outbreak, but I also want to talk about the late 1950s. Not because of who RD85 and its neighbor may have what they may have been experiencing at that time, but who they may have actually encountered in the woods. So there's a very special person for coastal spruce research walking around in the woods. In addition to Robert MacArthur, Ronald Davis was doing his seminal surveys of the coastal spruce fir forests in Maine. And so this is a map of the entire coast of Maine demonstrating where coastal spruce fir forests are from aerial surveys and ground surveys. Ronald Davis at the time in 1959 identified the 14 oldest coastal spruce stands along the coast of Maine that he could find. As part of my second century fellowship, we proposed to resurvey 7 of those stands. And so this is Sean Fravor and I pouring through Ron Davis's notes in the field, trying to relocate 7 of those stands that were on or near the park. And what we wanted to see is how are our forests changing over the last 60 years. So this is a map depicting the 7 stands that we were able to resurvey for part of this work. And these graphs here, it's kind of the like wow factor for how much work Camilla did to measure all of these trees. These are actually stem maps of the locations of every single tree in a 10-meter wide, so about 30 feet, and 200-meter long transect at each site. So that's about 2 football fields long. So these huge plots measured and mapped the location, size, species of every single tree. So while those are just kind of a wow factor, we can break that down to understand the dynamics and what's been happening in this forest using something called a diameter class distribution. This just simply shows along the x-axis the diameter of the tree at breast height in centimeters. And then the y-axis is showing how common that tree is on a per hectare basis. You can just think higher on that graph means more of those trees are in that forest. And we can see some patterns emerge. Why don't we zoom in on Bass Harbor Head, a space we were already introduced to. At Bass Harbor Head, you can see in 1959, that light green line, there were a lot of trees in this 10 to 20 centimeter diameter class, relatively small trees, but there were some bigger trees as well. When we came back 60 years later, there was a lot of regeneration, a lot of these much smaller sapling trees. And so this suggests that there was a major disturbance that occurred at Bass Harbor Head that's opened up the canopy and triggered some new regeneration. We can also see that at Ironbound Island in Western Mountain, there has not been a big change in the structure of those forests. These are depicting an old growth structure to their forest stands. So while we have some really large trees, we also have trees in all the other size classes below them, including a lot of regeneration. These are messy forests that have individual tree fall gaps that trigger and promote regeneration, an uneven aged forest structure. Let's take a look at what those actually look like on the ground. So on the left-hand side here, you're looking at Bass Harbor Head. You can see maybe there's Sean Fravor walking around. It's pretty dense in there. So there's a lot of stuff that's blown down, a lot of CWD, which is our coarse woody debris. There's a lot of standing dead trees, but also a lot of regeneration in that stand. Blackwoods, where we had that pollen sediment core from, has gone through kind of classic successional dynamics. And so this light green line is depicting that most of the trees were in this 10 to 20 centimeter diameter class. But over the last 60 years, we're getting fewer and fewer of those, and some of the trees are getting bigger. So as we have larger trees, they occupy more space, so we have natural self-thinning of the stand. And then over at Western Mountain here, you can see this forest also looks kind of messy, but we have lots of big trees, and there's a mix of regeneration in there. That's that uneven age structure that's typified of old growth structure in stands. So now that we've brought you up to kind of present day with how our forests are changing with some of the dynamics, we can think about what happened just a few months ago. So the coast of Maine just a few months ago experienced a severe drought. This is the US Drought Monitor map for kind of mid-August. And this is something that we're tracking and really closely watching, because with our tree ring studies, we find that tree growth really declines the year following a dry August. And so the year following a dry August is coming up for our spruce trees. It doesn't mean they're necessarily going to die, but on average, we expect them to grow less and less. As these drought conditions become worse and more common in the future, we suspect that those may be some of the factors that lead to progressive declines in our spruce trees. And that leads us to thinking about the future. So the Gulf of Maine is warming faster than 99% of water bodies on Earth. And the northeastern United States, the inland temperatures are also warming at really fast rates. This raises a lot of concerns for the future of our coastal spruce forests that depend on cool and moist conditions. Suitable habitat models, which I'll be talking about today, but also species distribution models, suggest that the outlook for red spruce is not good. Here, these dark red regions, you can see Mount Desert Island in the roughly center there. Those dark red colors represent current suitable habitats, so where red spruce could live based on the conditions experienced today. We can project forward to 2090, and you can see that there's none. And unfortunately, the story doesn't change if you only look forward to 2060. That's only 38 years from now. So just this graphic down here, the red colors there represent where in 2060 we will have no suitable habitat for red spruce trees in the future. It's kind of a scary thought, but that just means that we don't really understand. It's a new space for red spruce to be growing, and we don't really have a good understanding of what that might mean for those forests. But the habitat they're used to will not be present in those areas. And so that moves us to thinking about how those forests may persist or change throughout this period. And this is where I'm going to wrap up talking about how the forest canopy can help to nurture some of the regeneration in the understory. So we'll look at a scenario here as we move with an intact forest canopy today to 2100, if I just kind of pick an arbitrary future. If we at least expect, yes, the trees would grow, but expect that we have a relatively continuous canopy of spruce trees during this period, maybe the regional climate will warm about 3 degrees Celsius. Now, on a hot summer day, we know it's nice to step into the forest because it's cooler in the forest. And so today, maybe we get about a 3 degrees Celsius cooler forest understory where our regeneration is. If we maintain that forest canopy, it may lead to also a 3 degrees Celsius warming in the understory for our regeneration. That's if we have a continuous forest canopy. Now, if we bring in large-scale disturbance, it may change things. So here we're looking at the same situation where it's about 3 degrees cooler in the understory, but now in our future condition, we've got a disturbance. Maybe it was an insect outbreak, a windstorm, or a climate change factor that led to the decline of some of those canopy trees. We still have a regional warming of 3 degrees Celsius, but when you measure the climate in the understory, it's now warmed 5 degrees Celsius or more. Those are the types of events that we're trying to better understand and predict, because that can be the tipping point that causes our regeneration of our boreal type tree species to decline and more northern hardwood or more southerly species to move in. So today, we talked about the spruce family and how it got to where it is. We talked about how we still have a lot of spruce trees growing in our park, and they seem to be doing really well. But we certainly have an uncertain future for our spruce trees. And luckily, I can say that there's a lot of good scientists working on this question right now that can help us improve our understanding of the future of coastal spruce forests in Maine. Thank you.
We have a couple minutes for questions.
Hey Jay, this is Peter Nelson, Scudic Institute Forest Ecology Director. Great question.
Speak up.
Or great talk. I have a question about how the forest resilience could be measured. And there's a recent paper out about the genetic diversity in red spruce. And I just wondered what sort of, I don't want to say hope, but sort of resilience that we might not know about. And what kind of mechanisms in that diversity of the red spruce might facilitate survival in a warmer climate. And specifically, I'm thinking about fog and foliar uptake of water. Thanks.
Great, thank you, Peter. So Peter's asking about where's the hope? And is there hope in some of the genetic diversity of red spruce? Because it's a species that can grow much further south than it currently does, but it's primarily limited to mountains, for example, in some of those places. And also, you mentioned the importance potentially of fog. And those are excellent questions, and unfortunately at this stage, they're kind of unknowns in some ways. I think the genetic component is an important one, and there may be opportunities to bring new genetics up for species that may be able to survive in these warmer and drier conditions. But I think that can only take us so far, especially because the red spruce trees that grow further south still grow in these areas that are mostly cool and moist. And at the high elevations in mountains, they're often inundated by clouds. So that brings us back to thinking about the coastal fog influence here and how important coastal fog is for potentially maintaining the spruce trees along the coast here. I think we will have red spruce trees along the coast of Maine in 100 years. I think that's a given. The question is exactly where and how. And I think it's going to be these localized and smaller refugia is the term that we use for it, where there's local hydrologic conditions that allow for relatively cool conditions and also for them to avoid some of the stressful heat events and drought events that they receive in the summertime. And I think the coastal fog story is still a bit of an unknown. To be honest, I don't know the science behind the future of coastal fog. While the Gulf of Maine is still warming, anybody went swimming this summer, it's still pretty cold. And so I expect that we'll still have a large influence of fog. But I think there's going to be more disturbance and change around some of those events as we move to the future. So kind of danced around a little bit, but I'm glad that you brought that point up, that it's not all doom and gloom. It's change, but it's not the end for our coastal forests for sure. Thanks, Peter.
A quick question for you. More and more conservation biologists are taking a look at human-assisted migration of genotypes. So my former job in New Jersey, we did a bobwhite quail or northern bobwhite reintroduction, and we used species from the southeast, knowing that would be the suitable climate conditions. They're smaller birds, leaner for the pine barrens of New Jersey in 30 years. So as you look at these models, do you see that there are not just specific to spruce, but there is a role for human aided transport of genotypes to aid in long-term conservation?
Excellent question. So asking about how we think about genotypes and human intervention as our forests progress through this change. That's one of the challenges along the coast of Maine in particular, because a lot of our coasts we want to preserve and protect. And there's a lot of discussion right now around what's the best way to do that. Should we leave our forests alone and let it do its thing, or how should we be involved? And there is some work actually specifically for red spruce around looking for more climate resilient genotypes from further south. That work does not actually link up to the coast though. And so this coastal situation is kind of this unique space where we have this coastal influence from the fog and the cooler conditions where that may or may not be as important or as needed. And so that's kind of the unknown question that we have right now, where these coastal spruce forests provide a lot of important regional diversity in our forest types at this lower latitudes, the extent to which the climate change may or may not drive declines in those. So the short answer is yes, there is some work on that. It remains to be seen how well that can apply to the coastal situation. Good question, thank you.
One of the problems down south with the red spruce
Okay,
is
thank you.
Thanks.
Good morning. Can you hear me okay? Sorry.
There we go. John Daigle from the University of Maine. And this will wrap up our session on forests. We'll have plenty of time for questions after John. So if you have questions for any of the previous speakers that come up, we'll have a few minutes for that. And then we'll go into poster session. So thanks, John.
Yeah, good morning. I'd like to share some of the research that I've been involved with my graduate students at the University of Maine over the past nearly two decades. And it's really focused on integrating some of the environmental impacts caused by visitor use in areas and assessing, management responses to visitor impacts and assessing kind of the efficacy of how we're doing it in terms of management in our efforts. And I'm going to focus my talk with work that's been done on a very popular area, Cadillac Mountain. And this kind of ties in with, just thinking about parks in general, right? Where we have infrastructure, where we facilitate that use. And of course, with the road that leads to the top of Cadillac, the easier the access in general dictates more visitor use to those places. And for the short drive to Cadillac, I think most of us know the beautiful views that we can see on top of Cadillac Mountain. And it's something that's not new. This is an old picture of about the 1930s, 1940s, around Easter time, where we had visitors on top of Cadillac Mountain, pretty much filling the parking lot at that time, that point in time. And that kind of has continued to more present day, where it can be very busy on top of Cadillac during the summertime and increasingly more the fall season. And with that use, we do see environmental change occurring, right, with the vegetation impacts and trampling that's occurring on the vegetation. And typically, as a policy around managing visitor use and particularly high use areas, the more visitor use you have, the more intense the management might be, or more direct management that might be necessary to try to mitigate some of the impacts that might be caused by visitor use. And over time, there's been development of practices to try to reduce the impacts caused by visitor use. I think most of you may be familiar with the Leave No Trace program that initiated, really kind of started efforts in the 90s and 2000s, looking at the effectiveness of what we might want to say to have an impact on visitors' behavior. And through science, through research in other places, they've actually, have shown, even though we've had increasing numbers of visitors in some of our popular places, we've actually seen a reduction in visitor impacts. So some of the practices are making a difference. And there's other aspects such as putting barriers to kind of direct where visitors go. Acadia has had the Steward Summit program for educating visitors for many, many years now. And so there's been a combination of efforts at Acadia in particular since the 90s, where we really wanted to assess, is it making a difference? Are those management practices having effect on less of an impact with visitors visiting on top of Cadillac Mountain? And this is just a layout of some of the management approaches. This just shows where Leave No Trace signage has been put into place over the years, updated assessments of studies looking at people's reactions to those signs, looking at the language of the signs, that from having something that they read to having what we call Ghostbuster signs, where you just see a sign with a foot and kind of a thing through it, which actually seem to be more effective than having something for people to read. They just kind of see that sign with a slash through it. Oh, don't go there. And other kind of management strategies, trying to influence where visitors are going with some of the management strategies. So with the work that we've done, which started in the early 2000s with my student Min Kim, who is now at Marshall University, we wanted to assess the efficacy of management using remote sensing data, data that had been collected with aerial imagery back to 1979. So we were able to look at different years of impact on the vegetation. Again, at a high level, we're not at a species level, but we can actually, through science, start to detect vegetation decrease and increase in particular areas. So we basically set up an experimental design where the top part is actually the Cadillac Summit, including the Summit Trail, where there's visitor use. Importantly, you can see concentric circles where we have visitor use, because we know already that visitors sometimes don't always stay on the trail and they're off the trail. So we really wanted to get a broader scale assessment of impacts on vegetation with visitor use. That compared with a control site nearby with similar characteristics where there's no visitor use. And this is just a photo from 1979, kind of showing kind of the vegetation. You can see a lot of white, right, that's no vegetation where there's bare rock. And again, we were using high resolution data to kind of assess some of the vegetation change over time. And at the University of Maine, in our School of Forest Resources, techniques have been utilized and developed where we can detect vegetation decline and increases that we applied in our study. So again, you can kind of see it's, on the upper right, you can see the kind of concentric circles where we have the experimental site and the control site. And I know it's kind of hard to see, but with the blue, we have vegetation recovery detection, and we have vegetation impacts, which is more the red. And you don't see much blue and you don't see much red, right? Because again, when we think of Cadillac, at least for recovery, it can take a long time for vegetation to recover in a harsh environment, a subalpine environment. But we are seeing recovery occurring. And basically we were able to detect actually more increase in recovery of vegetation in our experimental site than in our control site. And we were able to detect, some of the vegetation impact that was occurring over the time period. But again, nothing that was really significant during our time frame. So in essence, the management that's been implemented over time has really kind of stopped or reduced the level of impact that we're seeing on top of Cadillac. And in some cases, seeing more kind of vegetation recovery, which might surprise some of you. And one thing that's really interesting that we found out with the work that we were doing was that most of the reduction in vegetation, or we see more vegetation impact, was actually occurring away from the Summit Trail. So when people were seeing the sign, or we had the barriers in place, the vegetation was holding its own and actually recovering in some cases. It was where we were away from the trail, where people get off the trail, where there's an avenue to get off, getting away from the trail. That's when they started to step on more of the vegetation away from the Summit Trail, which is a little bit different because typically we tend to see trails and the impacts getting larger from the trail itself. And I think that's one of the uniquenesses when we think about alpine settings, where you do have sparse vegetation, where you can kind of get off the trail, be on rocks, and then be near vegetation. So something that was kind of new in terms of kind of recreation ecology research and impact patterns, something we were kind of seeing different here at Acadia. That I think has some implications where we might want to have a little more assessment of maybe areas that might be popular away from the trail, where we might want to have more signage or protection of that vegetation. The other thing that we noticed, again, looking at this data through time and vegetation impacts, was this area up here with a noticeable decline in vegetation. And if you think about it, 80s, 90s, 2000s, there's been more popularity on bus tours, cruise ships, and there was a redesign of the parking lot during this time period where people were being kind of dropped off. This is kind of the designated bus area. And again, we didn't have any personal observations in this case, but we surmised that people, when they got off the bus, instead of going to the Summit Loop Trail, was kind of going right up to get a view of Bar Harbor as they departed the bus. And so I think some of the value of some of this high resolution data, looking at vegetation change over time, has some real value when we start looking at the potential of vegetation change with visitor use. We've done this study 3 times. The latest study involved the west parking lot area that we don't see in this area, but also observing some of the vegetation change there where there's less management in terms of signage and barriers. And we are seeing, we did see more vegetation impact in that area where there wasn't as much management attention. So this is just a picture of those bus stop locations are where there's recent efforts to revegetate this site, where we've kind of seen more noticeable change over the past few decades. And you can see the rope system here that is put in place to try to protect visitors from going onto that vegetation. And again, I have to give credit to some of the science and research that's been done in terms of assessing techniques with what visitors like and what they dislike. And this seems to be okay to visitors. The ropes kind of helping them go in certain places. It's not disruptive to the experience, and it protects the resource. So having input from visitors and their reactions to our management, I think, is incredibly important. But I think we also need to think about the implications of things that might happen based on the management that we do, such as trying to accommodate some of the buses, which we can do, but we might need to have more direct management strategies where they're dropped off, if you will. Maybe having a sign directing them to the Summit Loop Trail, or having these ropes to protect these places. And again, it can be a challenging environment, in subalpine environments, particularly with revegetation. It's going to take some commitment with resources, likely bringing up more soil because of the shallow soils, and some diligence. But I do think, with the revegetation efforts and what we've seen earlier where there was work done, it can kind of hold its own with active management. So I think there is hope for this to kind of take hold, and to revegetate parts of Cadillac where visitors are located. Again, it's just a challenging environment where it's so easy once that vegetation gets disturbed, losing the soil, and so you can have a rapid decline in vegetation loss where we have visitors walking on vegetation. This is more of a direct management style, right? It's kind of ropes, barriers, signage, but I think that's something that's going to be required as we think about the future, where we have lots of visitors in high use areas. If we want to protect those resources and also protect some of the important visitor experiences. I just wanted to briefly talk about more work that I think has implications and value of kind of the integration of social science with some of the ecological recovery efforts that is going on in Cadillac, but also importantly other places. This was a situation not too long ago, before the reservation system was implemented on top of Cadillac. And safety concerns, but also parking concerns that have been part of the visitor experience for quite some time. As early as studies back in the late 90s, generally visitors report very high satisfaction with their visits to Acadia, but consistently one area that they say things could be improved upon is parking and congestion. And that was back in the 90s, right? So, and we certainly experience that now. So as part of this, another student of mine, Becca Stanley, who works at Friends of Acadia, she's working on her master's project, and she assessed the experience of the reservation system with visitors. And not surprisingly, parking and congestion, the reduction of those things, easier to find parking, less congestion, rated very highly. It was actually more important than some of the other experience dimensions when people are visiting Cadillac. Obviously, kind of seeing this, the large view shed and other things rated the most important, but second or third was parking. So having that, I think, really, and being satisfied now with the parking, really, even though they might have had some issues with the reservation system, they still reported high satisfaction levels with their visit. Oops, so sorry. So again, thinking through how visitors are reacting, what they wanted, what they may not have wanted, such as the popular sunrise segment of, so what are the implications of this? In most cases, visitors who didn't get their first choice still reported very high levels of satisfaction with their visit to Cadillac. They still had access. But in some cases, you may have visitors who still want to see the sunset, maybe other places. And I think that just as we kind of see with some of our management actions, maybe saying, trying to accommodate with buses, I think we should be also thinking about the potential implications of visitor displacement or other areas as we think about the reservation system. And this is my last slide here, but it just kind of shows things that we might be thinking about, things that we might think about in terms of prioritizing inventory of vegetation and maybe change detection in our vegetation where we might see visitor use changing. Might be perhaps more increased visitor use accessing the summit with their trails. This could be pretty much during the whole day, right, when people can access, mostly during the daylight hours. And also, so perhaps more vegetation to work here, but also thinking about other trail segment locations where we might see people trying to access those trails for the sunrise. Thinking about not only here on the east side, but maybe on the west side when we think about the sunset and permits being fully taken in some cases. Where are people going for sunsets in Acadia? Are we going to see increased visitation in the west side of the park where that might be an opportunity? So, and I think with the remote sensing data that we have on vegetation, there's some real opportunity. We have baseline data, not just for Cadillac, but we can go back years looking at other places of the park. I think one of the obvious limitations is that you're going to be able to better detect vegetation change in a subalpine environment where you don't have a lot of tree cover. But when we think of Acadia in certain places that are popular with our summits, I think there's real potential for more use of remote sensing data, high resolution data for assessing this vegetation change. So I'll stop there.
Thank you, John.
Yeah.
I do expect we might have some questions for John.
Good morning. My name is Lynn. I'm from Friends of Acadia. My question for you is, I've noticed some signage changes you have mentioned earlier, especially on top of Cadillac, like the Blue Hill Overlook or Sunset Overlook is another section that used to have those names. Has removing those names give a more positive impact in changing some of those patterns so that there's less walkthrough through that?
That's a good point. I think those changes, basically have occurred since we had done our latest assessment for those places. So again, we could possibly look at, the effect of maybe, name changes to places and visitor use patterns. but that's a good point. But my sense is here, I don't know if I can answer that with the time periods that would kind of assess that vegetation change. But good point though, you know, in terms of the influence of management and things that you might be doing to kind of influence the attractiveness of areas or other things that's an important point.
Have you looked at the impact of the Hawk Watch traffic on that area that you pointed out where the buses park? That tends to be the main attraction for people. They see that Hawk Watch, that people have walked there. Because it's been my observation that people who go to the top of Cadillac in a bus don't want to hike the trails. They stay on the sidewalk.
Yeah. You know, that's a good point. You know, you're gonna have some people that even though you have signs that say, you know, Summit Loop Trail here, they don't know, maybe not know how long it is. So you could have some concentration of use in certain places. But again, I think things that could be considered is hardening or having areas that can sustain that visitor use where you know they're not going to go on the trails, but maybe there's another area where it's going to be good for them to see the view and still have a positive experience. Personal observation is something that, again, we have survey work that Becca did, but also just looking at the behavior of visitors once you start a new management system can be extremely valuable. Yeah.
Hi, my name is Catherine. I actually work at the visitor center for the park. And one thing we've noticed at the visitor center is we've had to redirect a lot of folks from Sunrise on Cadillac to other locations. Has there been any research into increased visitor use in social trails, say along Ocean Drive, because of the decrease in visitation to Cadillac for Sunrise?
Yeah, again, I think based on anecdotal evidence that I've heard from trail crews, we are seeing a shift in visitors and increasing numbers of visitors on certain trail segments that could certainly lead to more social trails or kind of going off designated trails. To me, it's a great opportunity to even get more feedback from trail crews to see which trails might be getting more use so that we might inventory more some of the resources or sensitive areas along that trail where we might see more effect of that increase in use. So I think that's a great idea, you know, maybe identifying certain areas where we want to monitor over the coming years. And that's one of the great things about some of the remote sensing data is that you have access to new data every year. So this could be something that's done more frequently than what we've tended to do, to come back every, say, 5+ years to kind of look at change and see how things are doing. It could be done on a shorter time frame. I highly recommend that, actually, with what you're suggesting. You know, if there are trails that are tending to get more use than they had before, let's see what's going on in terms of the effect on vegetation.
Hello, my name is Angie, and I am actually up on top with Hawkwatch. And so what's really interesting is different things of which I have seen since I've been up there for about 20 years, is that with the new reservation system, what's interesting with Hawkwatch is we have very little advertisement. So most people are literally just stumbling upon us because they are roaming. And many people now that they come up to the top of the mountain, is that they will only go down and use the trails, and not just Northridge trails, but I've heard them do it, heard talk of off over towards Southridge Trail. They're exploring more down those trails, only going a partial distance and then back up. Mm-hmm. So that seems to be, you know, one of the biggest changes which I've seen. I'm seeing people, and sometimes they stop in a second time, but they're definitely just kind of going down a little bit and then coming back up. And that to me on all of the trails all the way around there would also be a significant expansion of what they're doing and where they're roaming, where they're not necessarily supposed to be. Yes, we have on average only about 75 people per day that come out and visit, because most people do not come 200 yards down the trail, even with or without advertisement. So with that roaming, I would think that that is going to expand again on those outer ranges of what you've already found. They're going beyond the ropes and then going beyond that because there is no longer any ropes or signage. So that's an interesting perspective, which I've had up there.
Yeah, very valuable. That history that you have looking at those patterns of use is extremely valuable. One thing that I think is related to that is just the things that can be done through management action, and getting an assessment from visitors. And in most cases, if we do want to help direct visitors, protecting certain areas, protecting kind of revegetation efforts on top near where people are, I think it's showing some promise that I think we can be successful at it. It's still going to take education. It's going to take some time for that. I think that's especially important as we think about the effects of COVID and new visitors to our park, and it's the first time they've ever seen these no trace messaging. It does take time for that to kind of sink into people in terms of their behaviors in some of these environmental settings, but it can happen.
Thank you so much, John. Thanks so much to thanks to all of our speakers this morning. How about another round of applause for Jay and Vic? And now we have a poster session, which is across the lobby. And note that there will be different posters this afternoon. So make sure that you check out the posters this morning. And then we'll be back here at 11:15 for the next series of presentations. And the speakers will be around if you have any follow-up questions. And our friends on Zoom, we're going to keep the Zoom open, I believe, so you can just hang out, and we'll come back on a few minutes before 11:15. Thanks. We're covering a lot of ground today. For the next session, we're gonna come here to the Scudic Peninsula, and then we're gonna go back to Mount Desert Island to Otter Creek. Just a couple notes. I'm gonna do a couple notes about lunch now, just to make sure that we can sort of go right when we end at 12:15. So lunch is at Schooner Commons, which is out the front. Walk down the paths, there's signs, find someone who knows where they're going if you don't. It's just a short walk. And we want to kind of stagger our arrival at the dining commons a little bit, just so that there's not a huge long line. And so what I'm going to suggest is that two groups sort of go first towards Schooner Commons for lunch, and that would be elders. Elders, you know who you are. Please go get yourselves to Schooner Commons. And then I'm also going to request that the next group, those who are exhibiting posters in the afternoon, can get over to lunch so that they have time to get back and set their posters up. So poster session 2, folks and elders, let's let them go to lunch first, and then, kind of trickle in and just try to spread yourselves out a little bit. There are tables inside at Schooner Commons, and there's also picnic tables outside. So feel free to bring your tray outside and enjoy your lunch, because we have this beautiful weather that we've been gifted for the day. So now it's my pleasure to introduce my colleague, Seth Benz, Bird Ecology Director here at Scudic Institute, and he's going to share some information with us about biodiversity of the Scudic Peninsula.
Thank you, Catherine. Well, we all came to science in our own particular ways, and I'm going to take you back to 7th grade, my 7th grade, long time ago. I'm an elder. At least I get to go to lunch a little early. So I had a 7th grade science teacher who every day when we walked into 7th grade science class, he said, we're going to have a quiz. And so every day of the school year, we had a quiz. And so I'm starting you off with a quiz. Now, In my 7th grade class, we were paired, and you had to write down your answers, and then you would pass it to your partner, and you'd check each other. For this quiz, it's all up to you. So you don't have to shout anything out. You just keep the answers to yourselves, and the answers will come up, hopefully, through the program. So this is a biodiversity acumen quiz. How many species of ants do you think there are in Acadia National Park? That's the first question. So get that answer fixed in your mind, and we'll go from there. Second question, how many breeding bird species do you think there are in the state of Maine? That's number 2, breeding birds in the state of Maine. And how many vascular plants have been found in Acadia National Park? Those 3 questions, that's it. So today I'm going to talk about the biodiversity of the Scudic Peninsula, observational data sets, and long-term monitoring. So we all know, context-wise, what's happening with the changing climate. We have temperatures have increased, precipitation is up, and sea level is up. And Scudic is dynamic, right? We're talking about the Scudic Peninsula. It's cool, it's moist, it's a maritime climate. It's a transition zone between southern deciduous and northern coniferous forests. And it's dotted with alder thickets, dwarf shrublands, small bogs, and one major creek, which is Fraser Creek over by Fraser Point. Now, to take into account, we know that the Navy base was here from roughly the 1930s to 2003 or so, but not much scientific activity, at least documented scientific activity, took place during that time. In fact, if you quickly scan this particular slide, you'll see that a lot of things happened more formally from 1995 on. Prior to that, the information that we have on the Scudic Peninsula comes mostly from archaeological digs that found things like the great auk bones at Fraser Point or nearby. So the park took it upon themselves to establish this era of bio-blitzes, especially here on the Scudic Peninsula. And this was in part to round out or expand the work that was done by numerous people on Mount Desert Island, Proctor amongst them, the most prevalent amongst them. So here we established a partnership with the Maine Entomological Society and went about having bio-blitzes. And the idea behind them was to build upon a legacy of natural history study, not just here on the Scudic Peninsula, but across the whole park. Develop new science partnerships and increase awareness and excitement about biodiversity of the entire park. But also, most importantly, to establish new baseline information about non-charismatic fauna. So here's the answer to the first question. The ant bio-blitz was the first in 2003, at least from the records I could find. And 44 species of ants were found in Acadia National Park. How many of you got even close to that number? What an astute crowd. Very good. That's 6 out of 80 or so, maybe 10. And then from 2004 to 2010, insects and spiders of the Scudic Peninsula in Acadia National Park, well, this was undertaken. Again, with the Maine Entomological Society being the principal partner and people invited from around the country to come here to Scudic and explore the peninsula. So number of insect and spider species taken during bioblitzes on the Scudic Peninsula. Here you can see a bar graph that shows the various taxon that were explored and the numbers that were accumulated. Just give you a second to take that in. So in 2007, this one was interesting to me because it was the first time that it gave any sort of statistics about participation. So 58 participants took part, and it amounted to 2,553 volunteer hours. They discovered 151 species of spiders, 6 new state records, and 89 new species to Acadia National Park. These are observational studies in a traditional collecting style of bioblitz. So these organisms were in fact collected and preserved, and you can find records of these in the archives in Acadia National Park. So the whole idea behind this concept of bioblitzing was to expand citizen science activities. Obviously to up the interest in science and good science, and that might inform our resource management, and always underscoring the idea that education is the premise behind all of this. Education would lead to caring of the resources, caring for the park. So the era of those collecting traditional bioblitzes was from 2003 to 2016. 2016 was a transition that occurred. We went to, we partnered with the National Geographic Society and iNaturalist, and we held a bioblitz in concert with the traditional training. We used iNaturalist methodologies. Basically, iNaturalist, you use a phone or a tablet, you go out, take a photograph of an organism, and the organism is then can be identified by you, others in your party, or later on by identifiers that might be sitting around looking at these things. We all know that a bioblitz is an intensive survey of a defined area, inventorying as many species as possible in a short amount of time. So we got away from the targeted taxa to this all taxa methodology. So in 2016, there were blitzes that occurred all over the United States to mark the centennial of the Park Service. Our tools are principally iNaturalist and eBird through the remainder of this particular talk. So the statistics that I'm going to show originated through the use of one of these two tools. So on the Scudic Peninsula, iNaturalist observations since 2016. Total observations are under 20,000. The species documented are over 2,000 at 2,065. The number of observers that have contributed at least one photograph of an organism is over 1,300, close to 1,400. And the identifiers, people out there in the universe who like to look at iNat data and might help with identifications, is just under 2,000. And we see that insects on the Scudic Peninsula number 807 so far identified. Plants, which I believe was one of my questions for how many vascular plants have been found in Acadia. Does anybody know the actual number of that? So in my research, I found that it said in Acadia, vascular plants are 862. I don't know if Kate or Jesse actually know that that's close. But on the Scudic Peninsula, we found 724 so far. For fungi and lichens, 260. observations, or species, I'm sorry. Birds, 126 have been found, are documented. Spiders, 62. Mollusks, 34. Mammals, 24. Amphibians, 10. And reptiles, 7. So we have some work that we will continue to do and hopefully build some of these numbers. And then with this data, one of the handy things of iNaturalist is that every observation gets a location, and you can draw a polygon around the region that you want to look at. And this is a quick polygon of Scudic Peninsula, and you see all of the different locations there. In 2016, I also started a iNaturalist project that looked at all of Hancock County and Washington County combined, and the total number of observations there is closing in on 200,000 observations. This is pretty much without any sort of marketing or other than encouragement and word of mouth that happens through our social media, and anybody that comes to some of our programs might learn about these opportunities. So we're going to switch a little bit from the broader biodiversity to why we pay attention to long-term bird counts. Obviously, birds are sensitive bioindicators, and we have some really cool stories here in Acadia National Park. Number one amongst them is the return of the peregrine falcon. So we all know too much, and just recently the State of Birds has been published in this last week. This is a slightly older slide that says 28% of migratory birds are down, and we've lost 2.5 billion birds, and so forth, as this poster indicates. We are trying to keep track of the trends through our various bird surveys and documentation that go on here. So here at Scudic, over the last 10 or 11 years, we've conducted great backyard bird counts. We are keeping track of the spring arrivals of migratory birds, particularly warblers. We are doing breeding bird surveys. We have a hawk watch that is this year is its 28th year. And Angie King Johnston is somewhere in the audience, and she's our principal lead volunteer that has done that faithfully for years on end. And we applaud Angie for that continued devotion. And we have Sea Watch that takes place out here at Scudic Point, and a Christmas bird count. I'm going to quickly highlight those things. So in the Scudic general bird surveys, people have contributed over 6,000 individual checklists, and we've documented 252 species of birds. And then the hotspot list is below that, with the commensurate number of checklists and species seen at those particular sites. Sea Watch, which is taking place right now by Thomas Gagne, a student of COA. Yay, COA. So he's out there counting. We count from sunrise for about 3.5 hours up to 5 hours every morning, and some results from 2019. Really the thing to keep here, we've seen our low counts have been in the tens of thousands, but our high count in 2018 was over 105,000 migrating seabirds. That's loons, gannets, cormorants, eiders, sea ducks, that sort of thing going by. And the impressive thing about this is watching from roughly September 1st all the way to Thanksgiving, 250 birds per hour passing by Scudic Point. How many of you know that is happening? That's the end of my time. So quickly, here's a schematic of the flight composition. Talk to you later about that. And then the Scudic Point Christmas bird count, 50 years in running here in Acadia National Park. And the takeaways, these are quick. Winter bird populations are decreasing by 43% since 1971. This is including the Scudic Point bird count and Acadia National Park bird count. And you can see that I selected a handful of species. Actually, my colleague Kyle Lima, who's in the audience, selected these. And you can see the downward trends of some of these iconic species. Common eider going downhill. We see that southern species are increasing and northern species are decreasing, and the representative species there. But our conservation actions are working, such as the peregrine falcon, introduced in Acadia National Park in 1991, and you see that trend going up. We went from one introduced pair, there are now 3 active natural pairs that, to my knowledge, in Acadia National Park, and they're doing very well. And so, with that, I just want to say that daily observations of ordinary things and maybe not so ordinary things, and if you care to take a picture with your iPhone or document them in some other way, we can use that information. That's what you should be doing all day. Thank you so much.
We do have time for maybe one question. If there's anything burning for Seth.
Excellent talk. Thank you. Can you talk briefly about we've been talking a lot about Acadia and the park here, but migratory birds, for example, have a lot of other places that they really depend on. Can you talk a little bit about what you think the role of the park is in helping to conserve some of these species that use much broader areas than the park?
Great question. Thank you. I think primarily, other than, I mean, I sort of brought this interest in migration with me. I worked at Hawk Mountain Sanctuary and earlier in my career, started the Hawk Watch at Acadia. Sea Watch comes from Avalon, New Jersey, where they keep a Sea Watch. And so my vision was that we're up here in the northeast corner of the United States, and most of these known observatories are to our south, either inland, like at Hawk Mountain along a ridge system, or Cape May, New Jersey, which is obviously on the coast. We're a coastal site. What's happening here, and does anything that's happening here relate to what's happening at those places? And so, first and foremost, my advanced degree is in education, so I think I come from, let's educate the population about this. Acadia National Park is a perfect venue. Millions of people come here. Most people don't understand that there are millions of birds passing overhead every day, or spring and fall at least. And so I wanted to bring some of that attention to that massive movement. And then I just want to share the phenomenon of these migrations that are happening. And so that's my motivation. I'm pleased to have partners at the park that believe in that too, or at least encourage my tomfoolery. And so I'm thankful to all of those folks. Thank you for the question.
Thank you. Thanks again, Seth. And I would encourage all of you to use iNaturalist and eBird. One of the things that I've learned since working here at Scudic Institute is how important those databases are. Like, I think a lot of people think it's not really going to make a difference, but I talk to a lot of researchers who use iNaturalist. And they use it for their own work. And we've done our own analyses of iNaturalist to look at changes over time. So it really does matter, and it is valuable. So we're going to shift now to go back to Mount Desert Island and go to Otter Creek. We have a team presentation. Next team wants to come up of Hannah Weber, Marine Ecology Director at Scudic Institute, Chris Pearson from College of the Atlantic, and Derlin Lunt, Town of Mount Desert. You all gonna come up at once or? Okay, you're gonna start first and then they'll come up. Okay, so thank you. I'll get your talk up.
Thank you. Before I get started, Seth, where did Seth go? How many breeding bird species? I didn't hear the answer to that one. I know how many vascular plants and I know how many ants. Okay. Awesome. Thank you. Thank you. Thank you. Is that the advancing one?
That one with
Oh, the one
worn
that's
off.
completely worn out. Hi, everybody. I'm Hannah Weber, Marine Ecology Director here at Schoodic Institute. This is a talk about community science, and I want to note my incredible colleagues and partners in this effort. Darlene Lunt, the town manager for Mount Desert, Phil Lichtenstein, thank you, sustainability officer for the town, Abe Miller-Rushing, who is the science coordinator for the park, Rebecca Cole-Will, of course, is the head of resource management, myself, and Chris Peterson from College of the Atlantic. We will be giving this jointly. Derlin, I'm going to stand up here for a second and babble, and then I'm going to hand it over to Derlin. He's going to tell you an excellent story. I'll take it back to babble a little bit more, and then I'll hand it back over to Chris, who will tell you another excellent story, and then I'll wrap it up. So I'll be the last person up here, maybe Catherine, because she'll be kicking me off the stage before lunch. So with that, here's our talk outline. So the talk is perspectives on a community science project, thriving Earth exchanges, assessing health of Otter Cove, and potential pathways to remediate problems. So here's our talk outline. The heck is community science? What's the Thriving Earth Exchanges approach to community science? And what can we say about the health of Otter Cove? So, you know, a few minutes ago, Seth was talking about citizen science. I'm going to take sort of a little turn from citizen science to community science. So what is community science? Raj Pandya, who is the director of the Thriving Earth Exchange, you will hear us referring to this as either TEE or TEX through this talk. Community science is something that honors community knowledge. It is open science to change. It is humble. It is about how we value science in a larger community setting, knowing that the community is going to have a place for science, but it is going to be situated within their community. And really, community science happens when communities and scientists do science together that advances a community priority. And the priority for this particular community science effort comes from the history of Otter Creek. So Darlene's going to share with you a little bit of the history of Otter Creek. With that, I'm going to hand it over to Darlene.
This is okay. Which is the one on the computer?
Down.
That one. Okay. Thank you, everyone. I'm very glad to be here. My name is Darlene Lunt. I'm the town manager of the town of Mount Desert and have been so since 2010. I also grew up in the town of Mount Desert, attended the local schools there, so I have an interesting perspective. A lot of the things I'll be talking about today, I have lived all of my life because I have many of my school classmates were from the village of Otter Creek. Like Seth, I had a science teacher too, and that science teacher, if she were still here, would be very surprised to see me doing a presentation at a science symposium. But she would also be relieved to know that I'm not going to delve into any of the science of it. So I'll leave those to people that actually know what they're doing. Okay. you see in the left-hand side, let's see, where's that little thing here? Oops, so what? Technology is the one that's gonna lose that. I just wanted to get the way it was. I wanted to show you a little bit the seal of the town of Mount Desert, because it's very important in the context of what we're going to be talking about here today. That lime green section is the town of Mount Desert. And we list all of our villages around there. We have 6 very unique and divergent villages that more or less consider themselves to be towns as opposed to villages. And so I call the town of Mount Desert a very loose confederation of villages. And sometimes they also behave more like Greek city-states than villages in the town. So the history is fascinating there. This on here, oops, go back. This is Otter Creek Harbor, the western side here. The eastern side, rather, is in the town of Bar Harbor. The western side here is within the town of Mount Desert. So what we have to look at is how did we get to the point where we're all here today talking about the water quality of the community. So anyway, okay. Otter Creek today, if you're familiar with it and if you've gone through it, you'll notice it's more or less just a state highway going through. And you'll see a few stores, a motel, a nice restaurant when it's open, the burning tree. But many years ago, Otter Creek was a very thriving community with a lot of natural resource economy, including granite quarries, farming, fishing. It was not a natural harbor in the sense that it was a deep water harbor, but small scale fishing took place there. There was a lot of farming, saltwater farms around Otter Creek. And at high tide, you could actually bring a schooner in there to pick up granite and take it out. So it was a very thriving industrial farming fishing community. That is not the case today. It's more just a residential community. It's probably one of the smaller villages within the town of Mount Desert, but it has a very unique population, which is very proud. And Mount Desert is also, I like to call it, Mount Desert is the town where nobody comes from. And the reason I say that is because of that identification as villages more than a town. Okay, so I'm the town manager of Mount Desert. I live in Northeast Harbor. When I grew up, somebody asked me where I was from. I'm from Northeast Harbor. I wasn't from Mount Desert. And that's particularly true in Otter Creek. I think the folks over there are incredibly proud. Most of the families have been there for generations upon generations. And I think they have to take an oath of allegiance that if anyone asks them where they're from Otter Creek. They're not from the town of Mount Desert. So that's important to know. This is interesting. The population of Otter Creek, if you look over on the left, is actually going up. But the way that people make a living in Otter Creek has changed substantially. Up until the very early years of the 20th century, it was primarily, again, fishing, farming, working. Well, the quarry was pretty well defined. It moved over to Hall Quarry, it moved over to the other side of some sound, but there was mostly resource-based employment. That started to change during around the time of the First World War, where a lot of people then changed from being self-sufficient farmers, fishermen, etc., to working for summer people, summer residents in large cottages. So the employment base and the whole way of life in that village changed at that point. And that was accelerated during the Great Depression. Mount Desert, the summer residents of Mount Desert were pretty much recession-proof. The Great Depression, it affected a few, but most of the families that summered in Bar Harbor and over in Northeast Harbor, et cetera, were pretty much immune from the Great Depression. In fact, I only knew one or two whose ancestors jumped out the window in 1929. So they were the very much of the minority there. So right now we've got a village transformation. On the left is John D. Rockefeller, who was one of the prime donors of land to Acadia National Park. On the right is a trestle bridge that stands in where the causeway is currently located. And I mentioned the causeway a bit in a moment. Now, I know John D. Rockefeller was one of the more popular figures of Acadia National Park, but in the village of Otter Creek, he's probably not held in quite as high esteem, because most of the land in Otter Creek was purchased by John D. Rockefeller, donated to the park, which more or less shut the access to the harbor off from the residents. So the residents no longer had easy access to the harbor. If you've been over there today, you will see that if you know where Grover Avenue is in Otter Creek, there's a little road that goes down to a very tiny town landing. If there's no room to park, you have to, if you're taking a kayak down there in the back of the truck, you go down and then you have to back up and get out. So the access to the water is very much limited in that regard. So in Otter Creek, probably John D. Rockefeller Jr. is held in the same esteem as he was held by Theodore Roosevelt. I've heard the story, but Theodore Roosevelt called the first John D. Rockefeller the greatest criminal of the 19th century. So not a terribly popular figure there. Now we have the causeway, and you see those three little arches? Those arches are the only way that the tide flows in and out of Otter Creek Harbor. Very narrow constriction. And we believe in the village, or in the village of Otter Creek and in the town of Mount Desert, that this causeway is causing ecological problems in that harbor. And something needs to be done about that causeway. Now, hopefully we'll get more data out of the science project that Chris is going to talk about. But still, that is our firm belief that that restriction is a problem, and that causeway needs to be either replaced or redesigned to allow for a greater flushing of a beautiful natural resource. And the whole idea of this causeway is kind of the way it's built is kind of ludicrous if you stop to think about it. How many knows why it was built this way? Anybody? Yeah, Chris does. Well, now and Phil does. Well, now we're going to learn basically about that. This causeway was built with those three very narrow arches to allow tidal, because the whole idea was to turn that beautiful natural harbor into a swimming pool. Can you imagine today if that was proposed, how ludicrous that would sound? But that's why that thing is designed the way that it is. And the reason, what makes it even worse, is that the wealthy summer residents in Seal Harbor were tired of having Seal Harbor Beach being overutilized by tourists and natives. So here's what we'll do. We'll build this, turn it into a swimming pool, and hopefully many of them will go over there and swim over there. So there's a whole idea of just trying to locate people, tourists and stuff from one section of the town to the other. So it has a very checkered history, in my opinion. It's a pretty structure, but I think the damage that it's potentially done to the people in Otter Creek is tragic, and I think it's never too late to do the right thing. This shows a little bit more about the engineering of it. You can see the arches there over on the left. But the whole idea was, it never did get turned into a swimming pool, by the way. The baffles were never installed. So it's even worse. We never even got to use it as a pool. But so that is the history of the bridge and causeway. And so I've got the park officials here, and I know they're all going to help me, and Friends of Acadia and all these folks are really going to help me in my efforts to have something done about that causeway, and hopefully in the near future. That is some more. It just shows the engineering of it. Now, the other problem that we have over in Otter Creek Harbor is that up until from like 1975 or 6 until 2002, we had a sewage treatment plant. The technology of it got old. I don't think it was totally maintained properly the way it should have been. And so there's been some discharges of sewage into there, and there may be heavy metals and things as well. That's one of the things we also want to accomplish during this study is to take a look at the ecological health of that treatment plant. So we've got the two major issues that we're looking at, the causeway and the damage from the treatment plant. So the EPA gave it a very bad write-up. And finally, this is in white, the village of Otter Creek. As you can see, it's totally surrounded by Acadia National Park. It's the only one of Mount Desert's villages that would be totally surrounded by the parkway. And very, as I said earlier, very, very limited access to the water. So what we're hoping to do through this study is to have Acadia National Park, the town of Mount Desert, and the Bar Harbor part of Otter Creek all become natural partners to solve some of these issues. And I believe very strongly, I'm a big supporter of Acadia National Park. My uncle was a ranger here in the 1940s, so I'm certainly not anti-park. And he went down and became the superintendent down at Gettysburg. So I've got a long history of people being affiliated with the park. But you see, it's surrounded. And so I want the partnership. Right now, many people in the village of Otter Creek would consider the Acadia National Park to be a natural predator as opposed to a natural partner. And we're going to change that. And we're looking forward to it. Thank you very much.
Thanks, Darlin. All right, so if you're a community and you've got a problem, like how do you get some scientists to come along and help you with this? This is not a natural sort of meeting of minds, but it's not impossible. Luckily, there is this organization called the Thriving Earth Exchange. This is said, I will either refer to it as TEE or DEX. And TEX has a program that incorporates scientists into a community to help the community solve a problem that is a natural resources, natural hazard, climate change sort of problem. So there is an entire process that TEX has that allows these sorts of partnerships to happen. Projects always begin with a community voice. They are always built around community knowledge, and they always lead to community impact. These are community-driven, community outcome projects. Oops, and I went up instead of down. So here is our project team. We have the community leads, Derlin and Phil, community partner, Rebecca Colwell of the National Park Service, the community science fellow who really acts as the glue that holds us all together, Abe Miller-Rushing, and then community scientist, Chris Peterson, and myself. And with that, I'm going to hand it over to Chris to be the community scientist who tells you about some of the work that could happen to help the community solve these problems.
So you may think this is a microphone, but it's really a baton. So I'm a scientist, so I'm going to talk about social science process, of course. And so when we do this work, the first steps were that, as Derlin really pointed out really strongly, there have been concerns that the causeway was built in 1939. I don't know when those concerns first evolved, but when we got on the scene, they're clearly there. The first thing that then happened was what Hannah was talking about. Abe knew about these problems, and Rebecca, they talked to Mount Desert and they formed a partnership. And then they asked community scientists, myself, and then I asked Hannah to join on this project. And the sustainability committee that Phil chairs also had a lot to do with this work. Then we had meetings with individual community members. And then from those meetings, we then decided to have a group meeting with the whole community. This is the sign that the community put out outside our meeting when we were going to have our community meeting. And so, as you heard from Derlin, this is kind of the idea that this community has about this causeway. We had an exceptionally really good community meeting where we really tried to get an idea of what the questions were. Thriving Earth Exchange really has very little self-funding. It had a little bit. We use that to pay for, you guys might recognize Ron Beard in the background there. He's actually a resident of the Bar Harbor side of Otter Creek, but he's a professional facilitator, and Ron's done a great job of working with community in this. And I really appreciate Ron's work. I'm actually going to be in Bluebeck tomorrow, and Ron's going to be moderating that meeting I'm going to be at. From that work, Derlin wrote a memo out to the community. I just put the things that he highlighted. Some of them are not, some of them are not surprising to you. Is the sediment contaminated? The problem here was that when they built the sewage treatment plant, the line was supposed to go out into the subtidal. So it was supposed to go below the causeway and out. It ended up dumping in the intertidal. And so when the EPA came in 1997 to recommission it, and they saw that, they said, oh my God, you can't do this. And so at that point, the town had the choice of sending the line out or sending it over to Seal Harbor. And instead, that sewage treatment plant got closed in 2002, and it got sent over to Seal Harbor. And so that was a problem. There's no more contamination happening, but we have no idea if there's still contamination. Then there's a set of questions. There's the question about, clearly the causeway has affected flow. And so what has that done to the sedimentation in that area, and how has that affected the ecology of the area? Then there's a whole set of questions around biodiversity. And then there's a final question about climate change impact on the causeway. We know a lot about sea level rise, and we know that the causeway is vulnerable to that. Whoops, sorry. So then it was our job as consulting scientists to try to take this kind of information and be kind of like, I don't know, your car's GPS, and try to inform the community about the resources that they could have and how they could potentially get it to those places. So our job actually wasn't necessarily to do the science, but to tell them what kind of resources that they could have to answer those kinds of questions. And so when we actually wrote them a letter. We didn't give them this diagram, but when we wrote a letter back to the community in July, these are the ways we opened up the questions. For the sediment contamination, we reached out to Maine DEP. They were really good about being willing to work with the town, and so we handed that off to the town, and so Angie Brewer has been really excellent there. How much sedimentation has happened? We reached out to UMO researchers, to the park, but we also, throughout this, are also reaching out to more local groups like the MDI's Historical Society in Rady Bench and the COA Mapping Ocean Stories group about how you could potentially get this information, because information doesn't just come in terms of research, it comes in terms of all the information that exists. The oral histories, the log books, the pictures, all of those things. And then the climate change impact one, we just turned that one over. That was kind of a quick handoff on us, just kind of saying, yeah, this is on you a little bit, for lack of a better term. I'm going to highlight two of these. I'm going to try to get through this relatively quickly because we want to eat lunch, I know. The first one is how much sediment is the harbor compared to the past? Well, how does a community get that kind of information? In a lot of cases for sedimentation, you might be able to go out and get cores and look at how those sediments have deposited through time. Intertidal mudflats are really dynamic habitats. They're both bio in terms of organisms turning stuff over and in terms of flow. We don't really think that's going to be a very successful way to be able to do that, even though it's probably worth doing. But there's also a lot of information. When you go back into the writings about this area, you see people talking about access. You can see pictures. So this is a schooner at getting granite that's in the upper cove of Otter Creek. And so that's one of the places where Hall Quarry. So Hall Quarry actually had two quarries here before he moved over to Hall Quarry. And so those kinds of things can actually potentially give us information. And so those are the places that we think, that's one of the reasons that we think that groups like the Mapping Ocean Stories and Historical Society could be really informative on this work. The biodiversity questions, if you look at them, you'll realize that they fall into two kinds of categories. There's ones about the space and how the space has changed, so how Otter Creek has changed. But there's also then comparison questions. So this is actually a time question. How's it changed over time? And this is a space question. These are the moments that we would really love to have somebody like Jay, I think it was Ron Davis was the person that they mentioned. We would really like to have somebody that had done something a long time ago. And so we looked for that kind of data. And Seth actually really quickly mentioned William Proctor, who did a lot of work on the island in the 30s. Proctor did do some intertidal work and some dredging. And so this is from the Frenchman Bay Atlas. And all of these sites are places where he either dredged or did intertidal surveys. He did not do Otter Creek. So the other place, the Landscape of Change project from the MDI Historical Society that spent a lot of time looking at the Champlain Society logbooks. Both Rainey Bench and Catherine Schmidt here has done some great work with those logs. We don't think that there's really good information there. And so we really don't have information pre-Causeway that's really good information that we can get at in terms of these kinds of sources. The only really, so the times where we can actually find science, again, going back to somebody like Seth that said most of the data was from the 90s, we can find some data. And so this is data that Hannah Weber repeated with her group at Schoodic Institute. This really beautiful worm, you would never see it this beautifully because it's a couple of millimeters long in the mud. This is a really common mudflat polychaete, Streplospio benedicti. What happened is in the 90s, this is actually Otter Creek. This is the inner cove. This is where the causeway is. This is the ocean. And Hannah went back to these sites that they had done, looked at the abundance of just this species. They did everything, but we're just going to talk about this species. And what she found, although this is a log curve, so there's a lot of variability going to be there, they really didn't see any change in the density of this species over those 20 years. But remember, this is all post-Causeway. We really don't have that pre-Causeway data that we'd really like to have. So how can we get that pre-Causeway data? We actually think that the most likely places for that information is from the community, and the community can synthesize the information that they've already gathered. This community is amazing. As Derlin said, they really have an identity. They pull together photographs, they pull together logs, they pull together that kind of work. And we think that with a little bit of help from organizations, they can figure out what they really do have. And they may not have a whole lot, but they might have more than they think. So I think that these organizations, and these were the two that we recommended that they look at, but there's a lot of other places they could go too. But both of these groups have expressed interest in working with the communities and realize that this project started in 2022. Unlike the other projects today, we're just kind of in our infancy figuring this out. The other thing I want to talk about then is, do we have any science about stuff, especially about how these changes have happened? It turns out that the Bar Harbor Marine Resource Committee over the last several years, I'm actually chair of the Bar Harbor Marine Resource Committee also, has been looking at clam recruitment in several places in Bar Harbor. Over on the Western Bay in Blue Hill Peninsula at Clark's Cove and another place we called Windaway. Another two up in the Narrows around Thomas Island and around Hadley Point. And we've actually just happened to set up a site in Otter Creek. And so above the causeway, we have a site in Otter Creek. These are 3 years of data on how many little clams are around in the fall in the mud. This data was done by was really condensed by Emma Ober and Eliza Light, both for their senior projects at COA. And the one thing you'll notice is that the Western Bays have a little bit of soft shell clams. The Upper Bay has a ton. Otter Creek, we never pulled a clam out of a core. And so this kind of reinforces this idea that Otter Creek residents have, that there's something different about their cove, that something's happened there. We also put out these 1 by 2 foot boxes with screening on them as exclusion experiments to try to keep green crabs out. Sometimes green crabs still make it in. When we look in those boxes and see which boxes have green crabs, and this is for over a 3-year period, so these are just means for 2019, 20, and 21. These boxes are currently going to get collected in a week for 2022. And what you can see for green crab abundance is exactly the opposite pattern. So green crabs are an introduced species. They came to Maine probably on ballast water, and it looks like they really, really love Otter Creek. And so this is potentially really problematic for clams there, which is one of the things the community is concerned about. As a follow-up, one of the things we did this year, because we'd already started this project, this is now looking north, and so this is just below the causeway. We've actually added some experimental plots now on either side of the causeway, so we can start getting an idea if there's something going on there. And the other thing we're doing is towns have their own clam committees, and they don't necessarily talk to each other. And so we're trying to bridge that east-west gap by talking to the MDI clam committee. Just a last slide here before I hand it off to Hannah. This is just that same species again. What Hannah has also been doing is comparing different sites to each other. These are the data I showed you before, showing that that worm hadn't really changed. The comparative site, so this is Thompson Island, it actually shows the opposite pattern that you'd be predicting if Otter Creek was being degraded and had fewer of these worms. Historically, Thompson Island actually had more of these worms, and now they're down to the Otter Creek level. So this doesn't really support that idea. But now I'm going to turn it back over to Hannah so she can bring it on home and we can have some lunch. So here you go.
Thanks, Chris. I have 1 minute. I'm going to talk really fast. Right, I do want to point out that the Strebelus BO work was done by technicians and interns and scientists in parks at Schoodic. So I just wanted to sort of clear that up. There are some things, of course, that the community can do to address these biodiversity questions. Seth has already pointed out that there are tools such as iNaturalist. There are resources such as, joining a GMRI program that's focused on green crabs. There are tools available to this community, just like any other community, that can be applied to these questions and problems. It's just a question of honing in on where to put the effort that needs to be done to answer the questions that the community has. And also recognizing that these local changes in Otter Creek's inner cove are playing out against the same backdrop. We're all dealing with these global and regional changes, whether it's changes in sea surface temperature, ocean acidification, ocean phenology, loss of fisheries, increase of invasives, loss of mussels, and then of course the causeway, the wastewater treatment plant, changing demographics and occupations, all happening, in one place at the same time. We had that quote earlier about going out and getting mussels for bait. Now everything is dead. There are no clams or mussels from our community meeting. And we see that certainly in this Petratus and Dudgeon report from 2020, that there's this precipitous loss in mussels all over the Gulf of Maine. This was from Swans Island, but it's all over the Gulf of Maine. And this is the context in which the community of Otter Creek has to think about how to make change. The community has to accept that there are these global and regional changes, and that affecting change will occur at the local level. The community can't bring back a mussel population to anything above what the global and the regional circumstances will allow. But they can do a lot in that particular space. What happens next with this process, as Chris mentioned, we're right at the very beginning. The community decides on the next steps, and we as scientists are there to support them as we can in this process. This project and process will continue on as long as it needs to. It's been really interesting to be a scientist on this project. It's definitely sort of a new space for both Chris and me, which has been pretty awesome. And with that and going over a little bit, thank you. And if we have time for questions, happy to take one.
No time for questions. It's time for lunch. Elders, poster session 2 people, go on up to lunch first, and people in poster session 1, it's time to take down your posters. Thanks. Be back here at what is it? Back at 1:45.
Thank you for doing that.
I'm excited for the afternoon session. I hope you're excited as well. This is going to look a little bit different this afternoon. So Lauren Ross is going to, from the University of Maine, is going to start us off talking about circulation and water quality in Frenchman Bay. And then we're going to, Michelle Levine is going to join us via Zoom. So there's going to be just like a couple minutes of tech switch, and we can be having Q&A while that's happening. And then for closing remarks also will be Abe Miller Rushing will join us via Zoom. So there's just going to be sort of a little bit of switching around, but I look forward to learning more about Frenchman Bay's marine ecology. Scudic people, am I forgetting anything? So I'm like, my head is full from all of those posters and all of that great information. So I feel like I'm forgetting something, which I probably am. But I'll leave it to you, Lauren.
All right. Hi, everyone. Perfect. Thank you. So I'm really pleased to be here today to talk to you all about some of the research that my team and I have been doing in Frenchman Bay, particularly on studying circulation and water quality in the bay. So the title slide here has some of our interested partners as well as our funding agencies. And I want to point out that our team is made up of the Watershed Process and Estuary Sustainability Research Group at UMaine. We sometimes call ourselves the Whoopies group. So you can see our little emblem there on the bottom left of the screen. And I also want to point out that, you know, I'm listed as an author, but the first 2 teammates here are Taylor Bailey and Nick Tyner, who are the students who are doing the real heavy lifting for this work. And so Taylor is here today, she's a PhD student. Hopefully you got to see her poster this morning. And Nick Tyner is an undergraduate research assistant who's been working with us for like 6 months now. Okay, so what the Whoopies group is trying to do is really support decision-making related to water quality and shellfish industries. And we're focusing on coastal pollution and also harmful algal blooms. The objectives that we're trying to reach are understanding circulation patterns in the bay and the surrounding estuaries to help develop management decision tools. And in particular, that we want to understand the transport of material in the water. So where's it going? Where would coastal pollution go, and where would these harmful algal blooms go or be transported? And residence time, which is how long will it stay there? We also want to develop or are developing interdisciplinary partnerships, and we want to address this goal through knowledge co-generation with our interested partners. So we have several tasks that we've been really busily working on the past 7 years now, including the first one is getting baseline conditions or collecting data around the bay and in the surrounding estuaries. Because, you know, like you would think that there would be a lot of rich data sets for us to have, but really we haven't found a lot. So we're trying to collect data for baseline conditions of the bay. And then our second task is modeling circulation and transport so we can develop links to harmful algal blooms and coastal pollution. And then our third task is we're trying to develop a publicly available forecast for material in the bay that will be available online and will hopefully help to support decision making. Okay, so I'm going to really talk to you today about these 3 tasks that we're working on. And let's get started with the first one. So we started collecting data in Frenchman Bay in 2017. So we've been at it for a while, and our efforts have really ramped up the past couple of years. So there's a really busy plot on the top right of this screen. This is our study area. So you can see Frenchman Bay. There's a bunch of symbols and stars and circles and triangles and rectangles. And it's not important that you know what all those are, but just that you know that we're collecting data at all of those locations in the bay. And we're out there, you know, once a week right now for 16 weeks each year. Okay, and these data include current velocities that are collected with acoustic Doppler current profilers, so that measures velocity throughout the water column, salinity, temperature, and water level data, river flow, so we're actually gauging streams, and this is I like to call Sean Smith my freshwater counterpart. I study the coast, he studies the rivers. He's gauging streams that are flowing into Frenchman Bay for us. And we're collecting water quality data that now includes nitrogen, phosphorus, turbidity, ammonium, silicate, nitrate and nitrite, pH, and dissolved oxygen. And our partner from the USGS, Dr. Tom Huntington, is quantifying nitrogen loads from freshwater into the bay over the past decade. So he has those data. And I'm not going to talk a lot about those, but if you have questions, I'm happy to answer any questions that you have on our data collection efforts. And then we're also collecting data on harmful algal bloom cell counts, particularly pseudonychia, that creates domoic acid that can lead to amnesic shellfish poisoning if it's ingested by humans, and microplastics in the bay. So we're using these data to help calibrate, validate, and force numerical models to understand circulation in the bay. So here you can see a model simulation of the speed of the currents. So where it's red, that means it's really fast. And where it's blue, it's quite slow, or relatively slow, we can say. So you can see that you have really strong currents in the estuaries because it's a lot of water moving into like a really small area, right? So it speeds up, it accelerates. So once we have an idea of the circulation from the model, we can use the model output to figure out the transport of stuff in the water. Okay, so this is a really cool map that's just subdividing our study domain into different subdomains. So you can see that like each estuary, we have the Jordan River that's in red, Sullivan is purple, Frenchman Bay is green, and the delineations were made by Maine Department of Marine Resources during a meeting that was led by a PhD student of Sean Smith, B. Van Dam, because we were like, where does the estuary start and stop? Like, what are the important sub-embayments for you guys? So they actually on a map drew these lines delineating the different subbasins. So once we got that, we implemented particles in the model at the surface, mid-water column, and at the bottom to represent stuff. And our stuff is like pollution, so bacterial pollution, or it could be harmful algal blooms, or it could be microplastics, right? It's a proxy for things suspended in the water. Each one of the particles or they're evenly spaced and they have a tag and an ID. So we track where every single one of them starts, where it's going through time, and where it ends up. And that allows us to know if a particle is representing bacterial pollution that comes in from freshwater streams, where is it going to go and how long does it take to leave those delineated lines, right? So we can get residence time from that, or how long the stuff will stay in our subembayments, the connectivity between different subembayments, and also what's driving the transport of these particles or this stuff. Is it tides? Is it wind? Is it river discharge? And we're sort of trying to do a deep dive into the background physics to determine what those are. And so here, this is just an example simulation that shows some of the particle transport that's going on from one in the different estuaries and subembayments. And you can really see how these systems are interconnected, right? So from this, we're answering questions like, where are the particles transported? How long does it take them to get there? And what's the most important factor influencing transport? And some of our results from this study was recently published in a paper by a previous PhD student, Soheb Alamed, in 2022. So after we run these model or that simulation, what we end up with is a map for residence time. So this is a heat map that shows where you have residence time in days. So that's the colors, where it's red or warmer colors indicate longer residence times, and where it's green, it's shorter residence times. So some of our higher risk areas would be places that would take longer for the particles to leave. So this has implications for estuary pollution whenever you have long residence times in the estuaries, and it could also have implications for harmful algal blooms when you have long residence times in the bay. So first, let's talk about these implications for estuary pollution and some of the work that we're doing in particular for that. So this study is really led by Taylor. She is studying extreme short duration rainfall events. So we know that whenever there's a 1, 2, or 3 inch rainfall event in 24 hours, shellfish harvesting can be closed for up to 2 weeks. So we're just trying to inform or understand, where that 2-week mark came from. And what we're doing is we're using hydrographs from 10 different freshwater streams into Frenchman Bay. So these were collected by or created by Dr. Sean Smith and his team. So the x-axis here is days, the y-axis is stream flow in cubic meters per second, and that the peaks that you see at day 1, that's like the short duration intense rainfall event. So you have 1, 2, and 3 inches. And these red dots that you see on the map are the 10 streams where that fresh water is coming in. The background color is salinity. So where it's blue, it's more fresh. Where it's yellow, it's saltier. And this was a video I forgot to embed. Oh, no, it should work. Oh, it works. It works. Great. Yes. So here you can see the particles entering in from each of the streams. So we can tell, like, if these are proxies for bacterial pollution entering into the bay, how long is it going to take for them to leave? Right? And so this is in the works. Taylor's working really hard on this, and hopefully we're going to have some published results very soon. Okay, so now going back to the implications for long residence times in the bay, in particular for harmful algal blooms, Taylor and Nick Tyner, an undergraduate student, went on the bay with me to collect data on June 15th for a full tidal cycle. So we were on the bay for like 13 hours-ish, going back and forth collecting velocity data. The first figure that you're seeing is the tidal cycle that we were out, and we saw some really interesting things right at high tide. So at points 1, 2, and 3. So I'm showing you here at point 1, there's really small black arrows in there along the transect that we went back and forth with on the boat, and the direction of the arrows indicates where the flow is going along that transect. So the red ones are just to show you like a better indicator of where the flow is going at that time. So at point 1, you can see it's sort of like going in. At point 2, at the two extremes, it's wrapped around. And at point 3, they're sort of both going back the opposite direction. And this could be the turning of the tide, but we wanted to compare it to some of our model simulations of circulation. And whenever we compared it to that, you can see that there's a pretty pronounced circular pattern going on, or a gyre. And I drew the white arrow by hand for reference. Sorry, it's really embarrassing looking, but you can just to show or emphasize, what's going on in the bay at that location. So could this trap material? Well, we wanted to compare the location of that gyre to some of the harmful algal bloom cell samples that we had been collecting. So we have these two stations, station 2 and station 3, and now on the right is our harmful algal bloom cell count by location, where one of these little pucks equals 1,000 cells per liter. And we have 5 locations in the bay where we're doing our measurements of harmful algal bloom cells, and you can see station 2 and station 3 are indeed the highest, in particular, station 3. So it seems that the HAB cells accumulate in the center of this gyre. And we also wanted to see if there was any link to nutrients, because we are collecting nutrient samples as well. We did a first comparison with nitrogen and phosphorus. So now you're seeing total nitrogen on the top box plot and total phosphorus on the bottom. The x-axis is the different stations where we're collecting data, where station 2 and station 3 are in the center of the bay, and the other 3 are in estuaries around. And we can see that the total nitrogen and indeed the total phosphorus is really a lot lower in the center of the bay. And so this could be a result of it being lowest in the gyre because we have phytoplankton that are eating the nutrients. We're not 100% sure about that, but we are starting to establish links between HABs and nutrients and circulation, which is what we want to do. Okay. And then the final task is developing a forecast for decision support. So this is our numerical model domain that we're going to use that will be available online. It has more streams actually than the previous model. We've extended the domain all the way around Mount Desert Island. And what we're going to do is identify areas of interest to our partners to place particles. And we are going to come up with a 2-day forecast. So if we start with particles at one location, where are they going to end up in 2 days' time to hopefully help support decision making or management. And this will be available on the WHOOPIE's website. So that's our website, umaine.edu/watershed research. Feel free to email me also if you have any questions. And thank you. We have like a ton of also like other people that have helped out, and special thanks to our interested partners and yeah, shellfish farmers that have helped us out. And that was us trying to work our way through the mud. But thank you.
Thanks, Lauren. We do have time for questions.
How do you feel that this could inform making better decisions about finfish aquaculture using a numeric standard? So we're going to move the kind of politics and the different views people might have, but by way of establishing a baseline or citing criteria for making sound decisions that is based upon trying to minimize harm.
Right. Well, I definitely think that we need better monitoring for baseline conditions, because we're not going to know how things will change if we don't know how they are right now. And that's something that we're trying to do that'll apply to aquaculture sort of all around and all sorts of applications, even climate change, right? Because we need to be monitoring like yesterday, So hopefully, us establishing these baseline conditions and making those data available will be, useful for all of those applications. And, you know, maybe even our particle forecasts that we develop will help, you know, interested parties to look at the forecast to sort of understand where things will be transported, and that could come from an aquaculture farm. So does that answer your question? I think I saw it.
Can you talk a little bit about the third dimension? I don't know how these systems work, but kind of the depth and like things settling down, sedimentation and those types of processes, and how that may relate to these residence times?
Yeah, so we do, like, we model this all in 3D, right? And we have that our particles can be transported from one vertical layer to another. So we can capture those. However, we do not have that these particles have like a settling velocity, or they're neutrally buoyant, right? So they sort of are proxies for like parcels of water. And if we wanted to include, you know, like, let's say for microplastics, we're talking about actually like putting in diameters and masses to these, and including settling velocities to know where they would end up. But right now we don't really have it yet, but it's like in the future we would like to go there. Does that make sense? Okay. And then I did see a question about temperature.
Shannon, is there a question via Zoom? Do you believe there is any contribution of water temperature to the HAB and nutrient circulation data?
So I definitely think, so we're looking for links between both temperature and salinity and the harmful algal blooms. We haven't found anything that's, you know, really like bold evidence that there's a link with temperature in particular, but I do know that from reading some of the literature, there have been established links between temperature and also between salinity and the abundance of harmful algal blooms. Different species act differently. So we're really studying pseudonycha, which is one particular species. But I don't think I have any like hard evidence of that at the moment. Great, thank you, Lauren. You wanna?
You can shut your computer down if you want. Okay, now joining us via Zoom, Michelle Levine from Bowdoin College. Michelle, I think you can go ahead and share your screen.
Okay, great. Okay, can you see my slides? I
Not
see that
quite.
you cannot see my
Just wait a
slide.
sec. I'll tell you. I'll let you know when to go ahead, when to start. I don't know what I did. Okay. There we go. Go for it.
Okay, great. And you can hear me okay?
Yes, you sound great.
All right, excellent. Well, thank you for the invitation to speak today, and especially for the flexibility to do this over Zoom. I really wish that I could be there to meet everyone and see you all in person, but I do appreciate the ability to do this virtually nevertheless. So I'm going to be talking today about a project that we've been carrying out for the last couple of years in the Gulf of Maine. I was put into the session about Frenchman Bay, but I don't have a ton of data from within Frenchman Bay, but I think there are connections to the area and links to what some of the other speakers have talked about already. The work that I'll be sharing is a team effort. So I have colleagues who are mostly from the paleoceanographic community that are part of this, Branwen Williams, Al Wanamaker, Diana Thatcher, and Nina Whitney. We have a collaborator who's a geochemist at Bristol in the UK, who's Joe Stewart, and Aaron Strong at Hamilton College. And so The last speaker, Lauren, I have a great quote from what you just said. You just said that we need to be monitoring yesterday. And so that's what we're trying to do, is use paleoceanographic proxy reconstructions to put modern ocean acidification into perspective. Oops. Okay, so I know we have a relatively broad audience joining in person and on Zoom. So I just wanted to give a brief overview, a reminder of what ocean acidification is. So we know that atmospheric carbon dioxide has a warming effect on the surface, earth and ocean, but ocean acidification is often called the evil twin of global warming, in that same CO2, when it reacts with water, it can dissolve and have an acidifying effect on the ocean. And so without going over all the different chemical symbols that are shown here, just know that when CO2 interacts with water, it releases hydrogen ions. And if you remember from high school chemistry, the more hydrogen ions, the higher the concentration, the lower the pH and the more acidic the solution is. And so that's what CO2 can do to the ocean. We care about this because organisms that produce calcium carbonate structures like shells or skeletons, such as our clams, oysters, mussels, corals, these are all really sensitive to changes in ocean pH. And so when ocean acidification occurs or the pH drops, it makes it harder for those organisms to produce those structures. And if it gets acidic enough, they can actually dissolve. And so let's see here, I keep missing that. We've been measuring this over time in a few select locations. And so there are a couple of places where monitoring this has been going on really well, but not too many locations. And so here on the map is just showing a few of them. The nearest one to where we are is in Bermuda. And so the orange star is showing the location, and then the data here on the top panel are from that site. And then similar trends are seen in Hawaii and the Canary Islands as well. But basically what it's showing is since the 1980s, when they've been measuring the chemistry there, you can see that over time, so 1980s to the record here goes till 2015, atmosphere or ocean carbon dioxide concentration, although it's a bit variable, has increased over that time window. And when we look at what pH has been doing over that time, and so here on the right is the same site, but pH is on the y-axis and the same time series on the x. pH has also been increasing and decreasing from year to year, from season to season, but it's been dropping over that same time window. And so I wanted to point out a couple things from this figure. The first is that you notice there's a lot of variability or wiggles in the pH record. And so if we had not been measuring continuously pH over that time window with a high resolution time series, it would be rather difficult to discern the long-term trend. And so that kind of underlines the importance of having robust monitoring systems. But also I wanted to just point out the degree to which pH has changed at that site. So in Bermuda, if you were to take an annual average pH and plot that, it will help smooth out some of that seasonal variability. And you'll see that pH, the average pH has dropped by about 0.05 pH units since 1985 at that location. And so we're going to compare some Gulf of Maine data to that in a minute. These are just some visuals that I think drive home the importance of why ocean acidification is something that we should be concerned about. Many of you have likely heard of this effect before. These are from experimental results where when you grow organisms that produce shells or anything out of calcium carbonate, under varying CO2 and thus lower pH conditions, their structures respond to that and change significantly, where they're either thinner, disformed, they can not be as strong or robust, or just don't simply grow as much under higher CO2. And so, of course, here in Maine, we are concerned about this. We think that the Gulf of Maine may be particularly sensitive to ocean acidification, not only because we have valuable economic resources in our shellfish and aquaculture industries that might be affected by ocean acidification, but also the Gulf of Maine, because we have waters coming in from the north that are relatively cold and fresh. Colder waters can hold more gas and more CO2, and fresh waters have lower pH than those that are higher salinity. And so in addition to that, we also have a really strong seasonal biological productivity cycle, so that can affect CO2 and pH. And we also have a really strong seasonal cycle in terms of freshwater input from melt along the coast within the Gulf of Maine as well. So a lot of variability here where we are. And so in response to the potential threat of ocean acidification and the state of the science and the data, I just wanted to point out that there are, Maine is actually a leader in terms of at the state level responding and collaborating and bringing groups together to try to enact change around ocean acidification at the state level. And so there have been different iterations of folks that are thinking about this, it's a kind of a collaborative group of stakeholders from the fishing and aquaculture industry, scientists, legislators that have all been talking about this for a number of years. And most recently, this has been wrapped into the work of the Maine Climate Council that put out their report calling for more monitoring of ocean acidification or ocean pH in the Gulf of Maine. And then at the federal level, most recently, in summer 2022, President Biden signed into law the CHIPS and Science Act, which also included some really important ocean acidification legislation as well. And it authorized additional funding for NOAA ocean acidification program. And so I just wanted to note this because all of these works are really calling for more ocean pH time series and monitoring and identifying that there's kind of a gap in our data in order to respond to OA in some places. And so I've said that because really that was the motivation behind the collaborative project that I'll be kind of giving you an overview of and showing you some preliminary data from today. So when I was starting at Bowdoin was when a lot of the early discussions at the state level were going on. And I was really hearing from this diverse group of folks getting together to talk about this was that there really was a clear data gap where although there are a number of organizations and groups coming online monitoring pH data now, which is fantastic, we are still lacking kind of the historical baseline or pre-anthropogenic context in order to interpret those data. And so I'm a paleoceanographer, and I was sitting there thinking about this and wondering how we could use some of the tools in the paleoceanography field to potentially fill some of these data gaps. And so I reached out to colleagues of mine that I knew were working on organisms from the Gulf of Maine. And we thought about whether we could design a project that would help fill that gap. And so Al Wanamaker at Iowa State, who was at UMaine, he works on Arctica Icelandica or ocean quahog clams to reconstruct climate in the Gulf of Maine. And Branwyn Williams at the Claremont Colleges works on crustose coralline algae as a climate archive, and those grow in the Gulf of Maine as well. And so we got together and discussed trying to use a relatively new proxy, which is boron isotopes that is sensitive to pH, to attempt to reconstruct pre-industrial pH in the area, with the goal of kind of pulling the modern data and the pre-anthropogenic data together in order to address the policy questions that were being posed. So I'll just share a little bit about how these proxies work. We're trying to address this question of how has the Gulf of Maine pH changed over time. And so both the Arctica Icelandica clams and the crustose coralline algae produce calcium carbonate structures. So the clams produce these shells. Individual Arctica clams can live for several decades to centuries long. They've been used quite a lot for paleo climate reconstructions. And coralline algae similarly are time resolved. And so each of these you can see, if you look at a cross section of a clam or a coral and algae specimen, you can see that they have these annual bands like a tree. So each year that one of these organisms grow, it lays down a band. And not only can we look at the width of the band or figure out how much it grew, but also while it is laying down, or as it's growing, it's locking in information about the ocean conditions that it's growing in and records that as a geochemical fingerprint or change in chemical concentration or composition in each of those individual layers, and kind of records that over time. And so both of these organisms we know do this really well for things like temperature and salinity. And we're now trying to do this with boron isotopes, which we know are sensitive to pH. And so we can go in with our instruments and mill out samples from different years and figure out what the concentration of these different elements and isotopes are, and use that to back calculate out what the ocean condition was in a particular year. We have data from experiments where part of what we're doing with this project is trying to calibrate the proxies. And so we know that these isotopes that we're working with are sensitive to pH, but I'm not going to go into too many details about how the boron isotope proxies work right now, because I want to leave time just to show you some snapshots of some of the preliminary data that we have from these archives. And so I'll say that this is very much a work in progress, and we are still kind of filling in time series, parts of the time series, and we have different snapshots of different windows of time from different locations. But nevertheless, I think I wanted to point out the big thing that we're seeing, and that it seems really important, is the degree of pH variability when we compare the proxy records to the instrumental data. And so I'm going to show you the locations that we have specimens on the map. And then the color of the site marker corresponds to the scale bar here on the bottom right. And so what the scale bar is showing is not pH as a value, but the degree of variability in the record for whatever the time window is that we have so far from that data set. This scale bar up here on the left corresponds to the background map, so you can kind of ignore that. It's just the bathymetry of elevation. And so first, I'm just showing you two locations where we have instrumental pH data. One is from a NOAA buoy that's maintained by UNH, and the other is from Friends of Casco Bay that has a station near Yarmouth. And so these are just two examples for comparison. There are many more places that have pH data at this point, but what I wanted you to see here was that, so these are kind of color-coded blue, and so they are down within the realm of the degree of variability that you saw in that Bermuda record a couple of slides ago. So 0.05, I think one of these is 0.07 pH unit change over the time window that each of these have recorded. All right, so now I'm going to lay on top of this some early data from the proxy record. So we'll start in the north. So here in Jonesport, we have a series of clamshells that cover about 1999 to 2018. And you can see here with the orange color that these has a pH variability of about 0.2 pH units, which is quite a bit more than we've seen in any of the instrumental records. And we're starting to extend back in time a little bit. In addition, we have coral and algae specimens from two sites here in Penobscot Bay and not too far from MDI here, covering again two different time windows. And here again, you can see a lot higher, much higher degree of variability than the instrumental data, but also some important differences in terms of two nearby locations, although from two different time periods. And then lastly, we have the longest record, or the longest time window, represented from a series of shells from Seguin Island, which is a site that my collaborator Al Wanamaker has been working on for some time. And so I will point out here that this is not showing a continuous record from 1685 to 2010, but instead it's just a couple of points kind of scattered about through that time window. We're really working through the chronologies still, but what you can see from some of these sites, a 0.3 pH unit variability is really much more variable than we've observed in any of the instrumental records. And so that seems to be an important result as we go back in time and when we compare one site to the other. So basically these data are suggesting that although we're really still working on refining chronologies and proxy calibrations, and even within that uncertainty, these data have the potential to provide some important perspectives to instrumental records. There is also likely going to be a great deal of temporal pH variability and site by site or spatial variability among these records that would suggest that both natural and anthropogenic factors are affecting pH in these coastal locations. I did want to zoom in very quickly to two sites that are nearest to where you all are meeting today. So I think this is a great example of how two sites that are located only about 40 kilometers apart from one another are recording really different degrees of pH variability. And so there's a record from Eagle Island. Again, these are two different time windows, so it's not like a perfect comparison of one to the other, but I do still think that it demonstrates that the site on Eagle Island, which is shallower, it's within Penobscot Bay, maybe more directly influenced by riverine input, is demonstrating a greater degree of pH variability than some specimens that were collected from Duck Island that are more open, exposed location, maybe more directly influenced by Gulf of Maine currents and demonstrate less pH variability. And so this is important if we're thinking about where we want to set up monitoring stations and what the purpose of monitoring stations might be. You know, if you're interested in a clam flat that is, you know, located within Penobscot Bay, or if you want to set up an aquaculture farm somewhere, the degree of pH variability or the susceptibility to ocean acidification might be really different than something that's just slightly more offshore. And so this is important for us to keep in mind as we move into that sort of work. And so that was kind of an overview of where we are with the project. You know, we're still working on, what I'm not showing here is all the work we're doing in the marine lab. We have actually collected from some coral and algae specimens from Schoodic that we've brought back to the lab and are growing to try to refine the chronologies for these specimens with the hopes that we can get more detailed and kind of quantitative proxy to instrumental comparisons, but hopefully that is to come. We can certainly say that these changes in carbonate chemistry are likely not completely driven by ocean acidification, but instead, you know, this really spatially variable system is making it is likely more susceptible to local factors as well. And so we really need to improve our understanding of some of these factors, including things like even water masses that are coming into the Gulf of Maine, if those are changing, and considering localized monitoring that could help aid in adaptation efforts and identify vulnerable hotspots might be the way to think about monitoring. So thanks everybody for listening in and allowing me to share this work with you virtually. It's been a group effort for sure. There's an army of Bowdoin students that have contributed, especially to the experimental work in the lab that we've been doing. And I'd be happy to take any questions.
Thank you, Michelle. I'm not sure, hopefully you could hear that applause in the
I did hear
audience here.
some applause, thank you.
Okay, any questions for Michelle?
Hi, Michelle, it's Chris Peterson.
Hey.
You kept talking about variability of the samples at a sampling site, but for a lot of us, what we're really interested is in the directionality and how much of that variability is just noise versus how much of it is showing changes in pH over time. Could you talk about the relationship of those two things for us?
Yes, absolutely. So absolutely the goal of what we hope to be able to do is to show a plot over time, to be able to do something more like what we see in Bermuda, to be able to say like, yes, there will likely be some variability, but are the minima getting lower, or is there, you know, a trend or a baseline that we can compare to? And so we're really not at the point of being able to answer that question directly, like, is it increasing or decreasing and over what sort of time period? But I think based on what we've seen so far, I wouldn't be surprised if it's not going to look like the Bermuda record, that there'll be a lot more variability in the Gulf of Maine, especially the coastal in kind of near shore sites.
Okay, thank you. Michelle, if you want to stop sharing your screen so we can see all of you. Unfortunately, Chris Alexis is not going to be able to make it today and be with us. We will let you know when we'll try to reschedule his talk, and we'll let you know when that happens. And now I'd like to invite Acadia National Park Superintendent Kevin Schneider to say a few words of inspiration for all of us. And then Abe Miller-Rushing, who's on Zoom, is going to share some final thoughts with us.
Inspiration, Catherine. There's a lot of pressure here. I want to first start with thanking Catherine Schmidt and Emma Albee, Abe Miller-Rushing, who's on the screen, and Rebecca Cole-Will from our team for helping to pull this conference together. So how about a round of applause for all of them? I think it's great to see such a strong science community here for Acadia National Park. And I think this conference really embodies that. You know, after several years now of not being able to get to do this in person, it's great to see this community coming back together, and both online, but also in person, despite having to wear masks, despite being in a high COVID community transmission. You know, here we are back together. And it's great to see not just scientists, but educators here, folks from the Parks Interpretive Program, folks from outside the park who are educators, interacting with visitors, because, you know, science is really, really important to us as managers, and I can talk more about that, but it's also really important that we share the science with our visitors and with the public. We have an incredible opportunity here with 4 million visitors a year at Acadia National Park to be able to talk to them about the incredible work that's happening from a science perspective and build that science literacy among our visitors, because not all of them are PhDs, not all of them work in the science fields. And so I think it's just so important that we take the work that all of you are doing and help translate that to our visitors so that they can understand it, learn from it, and ultimately become more science literate themselves so that they can make good decisions in their own lives about science, whether it's wearing a mask, for example, or whatever it may be. And then, as I said, the work that you all are doing as scientists is incredibly important to us as managers. You know, in order to manage Acadia National Park, we need to make good science-based decisions. We need to make decisions that are informed by our community, by traditional ecological knowledge. It's too bad Chris wasn't here to bring the tribal perspective to this. But I think that's also really important. And so it's bringing all of this together to help us make really good decisions for the future of a place like Acadia National Park, which is so special, and people care so deeply about it. So thank you all for being here together in person. It's great to see folks. I'm going to turn it over to my friend and colleague, Abe Miller-Rushing, on the screen. So, hey, Abe, it's good to see you, and thanks everyone for being here.
Yeah, so following up from Kevin, I just wanted to say that I'm disappointed I wasn't able to make it in person. Can you guys actually hear me? I'm realizing. Can you hear me, Catherine?
We can hear you.
Okay, great. So I'm really disappointed that I wasn't able to make it in person. This is normally my very favorite event of the year. Unfortunately, COVID caught me and my family at just the wrong time. So I'm joining remotely, but I had a really good time joining remotely. And just to echo what Kevin was just saying, that the work you guys are doing, incredible work in Acadia. It really is helping us inform management and our communications. And as was kind of represented in a lot of the talks today, you know, we're hoping that it's not only informing us today, which it is, but that it'll inform management decades and even centuries from now, as you could see from folks revisiting work that was done decades and centuries in the past already. And so we want your work to be that kind of historical work going forward. And so I'll just wrap up by saying thank you to all the speakers. So for Stephanie Sparrow, who started us off last night, talking about how fall is becoming more unpredictable and with big impacts for ecology and fall visitation. And then for the speakers today, talking about the coastal forest, the Scoodic Peninsula, Otter Creek, our marine systems, and for all the poster presenters. So thank you guys very much for sharing your science. And I want to also echo Kevin's thank you to the organizers. Emma Albee did most of the heavy lifting for the organizers, but also Catherine Schmidt for stepping in and helping to moderate, Sarah Lucchini, Nick Fisicelli, Rebecca Colwill, Megan Mosher, and the team that helped out behind the scenes. Oh, Roy Gott with the technology. So thank you guys very much for making this happen. And as a last kind of just note that we'll be sending out a follow-up email with links to the recordings from today's talk. We'll be sending out an attendee list. And with that, I'll thank everybody for coming. And really, again, thank you for all that you do for Acadia National Park and also for stewardship and science more broadly. We really appreciate it. And the park wouldn't be what it is today without your work. So really appreciate it and thank you, and have a very good afternoon and stay healthy and safe.